Some few years ago, astronomers scanning the sky for asteroids stumbled upon something that defied all logic. A mysterious, cigar-shaped object hurtling through our solar system at an incredible speed. Unlike any known comet or asteroid, this interstellar visitor, named Oumuamua. It accelerated unexpectedly, showed no visible signs of a tail like a typical comet, and had a shape that seemed straight out of science fiction. Some scientists believe it could be a peculiar natural object from deep space, while others suggest something far more shocking. Could Umuamua be an artificial probe, a relic of an advanced alien civilization? Was it a lost fragment from a distant star system, a piece of alien technology, or something even stranger? Join us as we uncover the mind-bending theories behind Oumuamua, the alien asteroid that still baffles the scientific community. Before scientists started diving into wild science fiction theories, astronomers focused on gathering solid facts, things they knew for sure. The first undeniable truth about Oumuamua was that it had come from a completely different solar system. Something must have gone terribly wrong in its home system, perhaps a violent collision or a gravitational disturbance that sent it hurtling into space, eventually leading it to pass through our own cosmic neighborhood. But what exactly was Oumuamua? That was the mystery. Scientists weren't sure if it was a comet or an asteroid. At first glance, this might not seem like a big deal, but in astronomy, the distinction is crucial. Both comets and asteroids are space rocks that orbit a star, but they have very different characteristics. Comets are often called dirty snowballs because they are made mostly of ice mixed with dust and rocky debris. When a comet gets close to the Sun, the heat causes its icy surface to turn into gas, releasing dust and forming a bright, glowing tail that can stretch for millions of miles. These tails make comets some of the most spectacular objects in the night sky. Comets usually follow long, stretched-out orbits, taking them from the farthest reaches of the solar system and occasionally swinging close to the Sun before heading back out into the cold darkness of space. Asteroids, on the other hand, are mostly made of rock and metal. They are the leftover building blocks from the early days of the solar system and are mostly found in the asteroid belt between Mars and Jupiter. Unlike comets, asteroids do not develop tails because they contain very little to no ice. Their orbits are usually more circular and stable compared to the long, looping paths of comets. Based on where Oumuamua came from, far beyond our solar system, it should have been a comet. Objects from deep space tend to be icy because they usually come from extremely cold regions. But there was a problem. Oumuamua didn't behave like a typical comet. It had no glowing tail, no visible gas emissions, and none of the telltale signs that would confirm it was an icy wanderer. Instead, it looked more like an asteroid, just a bare rock tumbling through space. So the big question remained, what exactly was Oumuamua, and why didn't it act the way scientists expected? It is truly astonishing that scientists were able to spot Oumuamua at all, given the mind-boggling vastness of space and the immense scales of time at play in our galaxy. Stars exist for anywhere between millions to billions of years, and the process of forming an entire solar system takes hundreds of millions of years. Even the fastest-moving celestial objects require tens of thousands of years just to travel from one star to another. Now, compare that to humans, We have only been using telescopes to observe the skies for about 4 centuries, which is nothing more than a brief moment in the grand timeline of the universe. Even more remarkable is that only in the last few decades, or perhaps just the past few years, have we developed the advanced technology necessary to detect and track small, fast-moving, and faint objects like Oumuamua. One of the biggest questions scientists asked was, where could an object like Umuamua have come from? It is very unlikely that Umuamua came from an old, stable solar system. The reason is simple. Such systems don't throw out enough material to fill the galaxy. Once in a while, a rock might get flung into space, but it's rare for one to travel such an enormous distance. Young solar systems, on the other hand, are much more chaotic. In these systems, planets are still forming, colliding, and shifting positions. This creates a perfect environment for objects to be ejected into space. Small rocks and debris move around constantly, making them prime candidates for being pushed out of their home system. The solar system that sent Umuamua on its journey probably had a massive planet similar to Jupiter. A planet of that size has powerful gravity, which can pull, push, and even launch smaller objects into interstellar space. However, not every solar system forms a giant planet like Jupiter. In many cases, massive planets end up extremely close to their stars, turning into what scientists call hot Jupiters. These giant, scorching planets orbit tightly around their stars and are far less likely to fling debris into space. But there's another possibility. Neptune-like planets might have played a role. These planets are not as massive as Jupiter, but they tend to form in the outer regions of a solar system. In our own solar system, for example, Neptune helps shape the Kuiper belt, a distant region full of icy comets and rocky objects. In a young solar system, planets like Neptune could interact with space debris, shifting their orbits or even sending some objects flying out into space. However, finding Neptune-like planets in other solar systems has been a challenge. Our current methods for detecting planets work best when they are large and orbit close to their stars. This makes it much harder to spot Neptune-sized planets that are farther away. If Umuamua was ejected from a young and chaotic system, it likely came from a place where powerful gravitational forces shaped its fate, one with either a massive Jupiter-like planet or a distant Neptune-like one influencing its journey. Umuamua was also linked to a fascinating idea about how life might have started and spread across the universe. This idea is called panspermia, and it suggests that life isn't just confined to Earth. It could exist all over the cosmos, hitching rides between planets and star systems. The idea of panspermia suggests that life may not have started on Earth at all. Instead, this theory proposes that tiny life forms, such as microbes or spores, traveled through space and landed on Earth, where they eventually evolved into the complex life we see today. These microscopic travelers could have hitched a ride on space dust, meteoroids, asteroids, comets, and even spacecraft, some of which may have accidentally carried bacteria from one planet to another. Panspermia does not try to explain how life began in the first place. Instead, it focuses on how life might spread from one place to another across the vast reaches of space. The theory comes in different forms, including Radio-panspermia, Lithopanspermia, and directed panspermia. Regardless of the method, the idea remains the same. Life can survive in space and travel between planets and even across entire solar systems. One way this could happen is through planetary collisions. When a planet or a moon that contains life is hit by a large asteroid or comet, debris from the impact can be thrown into space. If microscopic organisms are trapped inside this debris, they could survive the journey, floating through space until they crash onto another planet. If conditions are right, these tiny life forms could start growing and evolving in their new home. Many scientists do not accept panspermia as a mainstream explanation for the origins of life. One major criticism is that it does not actually answer where life originally came from. It simply moves the question to another planet or moon. Another problem is that panspermia is difficult to test in experiments. Without direct evidence, it remains more of a fascinating possibility rather than a widely accepted scientific fact. However, some researchers are exploring mathematical models that show how life could naturally move between planets. This has kept the idea alive, even though it remains on the fringes of scientific discussion. Throughout history, panspermia has also been linked to speculation and hoaxes, often following reports of mysterious meteorite falls. A related but more widely accepted theory is pseudo-panspermia. This idea suggests that while fully formed life may not have traveled through space, many of the organic molecules needed for life, such as amino acids, could have originated in space and then landed on planets, helping to kickstart life. The idea that life came from space is not new. It dates back to the 5th century before the Common Era, when the Greek philosopher Anaxagoras proposed that the entire universe was full of life. He believed that life on Earth began when seeds from space fell onto our planet. The modern version of panspermia, however, emerged much later. The term panspermia was first used in the year 1908 by Svante Arrhenius, a Swedish scientist. Even before that, in the 1860s, several famous scientists, including Sir Fred Hoyle and Chandra Wickramasinghe, began exploring the idea more seriously. During the 1860s, 3 major scientific developments pushed scientists to rethink the origins of life. The Kunt-Laplace nebula theory. This theory suggested that the solar system formed from a cloud of gas and dust. It implied that early Earth was too harsh for life, meaning that life could not have emerged at the same time as the planet itself. Charles Darwin's theory of evolution. Darwin's ideas explained how species change over time, but did not address how the first life began. In his book on the origin of species, Darwin avoided this question. Louis Pasteur and John Tyndall's experiments. These scientists disproved the idea of spontaneous generation, which had suggested that life could randomly appear from non-living matter. Their experiments showed that all life must come from pre-existing life. This created a problem. If life could not just appear out of nowhere, then where did it come from? Some scientists believed that life must have gradually emerged on early Earth from simple organic molecules, a theory now known as abiogenesis. Others, however, thought that life must have come from somewhere else and traveled here, keeping the idea of panspermia alive. In the year 1871, Lord Kelvin, a famous physicist, proposed an interesting idea. He suggested that just as seeds are carried by the wind, life could be transported through space by meteorites. If a meteorite contained living organisms and crashed onto Earth, those organisms could begin to grow and spread. Kelvin also believed in a concept known as philosophical uniformitarianism, the idea that the same natural laws apply everywhere in the universe. He argued that life must always come from life, much like how matter cannot be created or destroyed. However, not everyone agreed with him. A German scientist named Johann Söllner challenged the idea. He pointed out that any organisms inside a meteorite would likely burn up while passing through Earth's atmosphere due to the intense heat. This made it seem unlikely that life could survive such a journey. Despite criticism, the idea of panspermia continues to inspire curiosity and research. While many scientists favor abiogenesis, the idea that life began on Earth from non-living chemicals, others still wonder whether life might have come from beyond our planet. The search for microbial life on Mars and icy moons like Europa and Enceladus is partly driven by the question, did life exist elsewhere and travel here? If scientists ever find microscopic life outside Earth, it could provide crucial evidence for panspermia. Until then, it remains a fascinating mystery, one that challenges our understanding of where we came from and whether we are alone in the universe. Long ago, scientists fiercely debated how life began on Earth. One of the key voices in this debate was a Swedish scientist named Svante Arrhenius. He strongly disagreed with the idea that life could have simply emerged from non-living matter, mainly because at that time there was no solid experimental proof to support it. Instead, he believed that life had always existed somewhere in the vast universe and had traveled across space to reach Earth. Arrhenius dedicated himself to figuring out how tiny life forms could move from one planet to another. Around this period, scientists had recently discovered that light from the sun could exert pressure on objects, pushing them with a gentle but constant force. This led Arrhenius to propose that microscopic life forms, such as bacterial spores, could be carried across space by this radiation pressure, traveling through the cosmos like invisible passengers riding beams of sunlight. This idea gave the panspermia theory a possible way for life to spread between planets. However, many scientists remained skeptical, questioning whether these spores could survive the harsh conditions of space for long periods. The theory also faced another major hurdle. It was difficult, if not impossible, to test in a controlled scientific experiment, a challenge that still exists today. Despite these doubts, the theory gained support from two prominent scientists, Fred Hoyle and Chandra Wickramasinghe. They believed life might have started elsewhere in the universe rather than on Earth for two main reasons. First, conditions for life's emergence might have been more favorable beyond our planet. Second, they noticed that life on Earth had certain characteristics that were hard to explain if it had originated here. Hoyle, in particular, studied the light patterns coming from interstellar dust clouds and found signs of organic molecules, which are the building blocks of life. He suggested that these molecules could have been part of a natural chemical process that eventually led to the formation of life, but not on Earth. Instead, he believed that comets, which are packed with ice and organic material, were the most likely places where this process could have occurred. Hoyle and Wickramasinghe also introduced another bold idea. They suggested that viruses from space could have played a role in shaping evolution on Earth. They believed that when comets passed near our planet, they could have showered Earth with viral material, introducing new genetic information that influenced the development of life. In a lecture at Oxford University on the 16th of January in the year 1978, Hoyle even claimed that major epidemics on Earth seemed to coincide with close encounters with comets. This idea was highly controversial and faced strong criticism from biologists. By the 1970s, advancements in space exploration allowed scientists to gather new data that could help test the panspermia theory. Although it still hasn't been fully proven, the idea continues to be explored through mathematical models and scientific discussions. Its long history shows that it remains an intriguing possibility. One version of panspermia, called Lithopanspermia, suggests that life could travel through space inside meteorites. According to this idea, bacterial spores or plant seeds might become trapped inside a rock ejected from one planet due to an asteroid impact. This rock could then drift through space and eventually crash onto another planet, where the spores or seeds might survive, take root, and spread life. Scientists have also explored whether certain types of meteorites could create environments suitable for life. Some theories suggest that heat from radioactive elements inside these space rocks could melt ice, providing both water and energy, two key ingredients for life. In fact, some meteorites discovered on Earth show signs that they once contained liquid water, hinting that this process may have occurred in space. With so many rocky bodies floating in the solar system, some scientists believe that many of them could have once been temporary homes for microscopic life. If one of these space rocks was knocked out of its original orbit and sent toward Earth, it might have delivered the first seeds of life to our planet. Plant seeds have also been considered as potential space travelers. Some plants produce seeds that can survive extreme conditions, including the vacuum of space, freezing temperatures, and exposure to harmful ultraviolet radiation. These seeds are not believed to have formed in space, but could have originated from another planet and been carried through space by natural events. Even if they were damaged along the way, they might still have the ability to sprout and grow in a new environment. There is also evidence that certain plant cells can repair themselves after being damaged, which raises the question of whether broken plant material could help spread life. Additionally, some plant cells contain tiny symbiotic organisms that could be released into a new world, potentially influencing its ecosystem. However, scientists continue to debate whether such seeds or spores could truly survive the long journey through space and the intense heat of entering a planet's atmosphere. Another possible way for life to spread across planets is through human-made space probes. Some microorganisms, like Tersicoccus fenicis, are incredibly resistant to cleaning procedures used in spacecraft assembly. This means that despite the best efforts of space agencies to prevent contamination, tiny life forms might still hitch a ride on spacecraft, potentially introducing Earth-based organisms to other worlds. While panspermia remains a theory rather than a confirmed fact, it continues to capture the imagination of scientists and the public alike. If proven true, it could change our understanding of life's origins and suggest that Earth is just one of many places in the universe where life has taken root. The idea that life can spread across the universe through space is known as panspermia. Scientists divide this concept into two main types. The first, called interplanetary panspermia, suggests that life can travel between planets within the same solar system. The second, known as interstellar panspermia, proposes that life can move between completely different star systems. Within these categories, different methods have been suggested for how life might survive such journeys. One of the earliest theories was introduced by Swedish scientist Svante Arrhenius in the year 1903. He called it Radio-panspermia, the idea that tiny life forms, like single bacterial spores, could be pushed through space by the pressure of starlight. Light, although weightless, can exert a force on objects. Arrhenius calculated that if these particles were smaller than 1.5 micrometers, they could be carried through space at high speeds by this radiation pressure. However, because this force weakens for larger objects, it would only work for extremely small life forms. Not everyone agreed with this idea. Scientists Iosif Shklovsky and Carl Sagan pointed out a major problem. Space is filled with deadly radiation, including ultraviolet rays and X-rays, which could easily destroy unprotected microorganisms. Even if billions of these tiny life forms were released into space, most would not survive the harsh conditions. However, some supporters of the theory believe that if even a few managed to endure, they could eventually land on a new planet in another star system after traveling for as long as 1 million years. Experiments conducted in space, using missions such as ERA, Biopan, Exostack, and Expose, provided important insights into whether microorganisms can survive in space. These studies showed that spores from bacteria like Bacillus subtilis were destroyed within just a few seconds when exposed to the full force of space conditions. However, when these spores were shielded by materials like clay or meteorite dust, they managed to survive for as long as 6 years. This suggests that if life were to travel through space, it would need protection, such as being encased inside rocks or meteors. For a microorganism to survive cosmic radiation, scientists estimate that it would need to be inside a rock at least 1 meter wide. Without this protection, exposure to solar radiation would break apart DNA and RNA molecules, making it impossible for life to endure. Additionally, the vacuum of space itself can cause severe damage to DNA. Because of this, the idea that life could move between planets or stars purely through the push of starlight without any protective shielding is highly unlikely. While radio-panspermia remains a fascinating theory, it faces significant challenges. The biggest obstacle is space radiation, which can easily destroy unprotected life forms. However, the idea that life might hitch a ride inside meteorites or dust particles and survive for millions of years is still being explored. Scientists continue to study whether the seeds of life might be scattered throughout the cosmos, waiting for the right conditions to grow on a new world. Scientists have long speculated about whether life could hitch a ride on space objects like comets and asteroids to travel through the solar system and even beyond. One idea suggests that tiny life forms, such as spores protected by thick outer layers, might be carried into deep space by comets. However, we do not yet know if this method is possible. Another concept, known as Radio-panspermia, proposes that microbes could spread through space via radiation pressure. But so far, there is little solid evidence to fully support this theory. A more widely discussed idea is lithopanspermia, which suggests that life could travel from one planet to another by hitching a ride inside rocks blasted into space by powerful impacts. Some scientists even speculate that life could move between star systems on wandering planets or moons, sometimes called nomadic exoplanets. However, this idea remains highly theoretical. While there is no direct proof that life has been transferred between planets in our solar system, scientists have been able to test some parts of the lithopanspermia process in experiments. The journey involves several major challenges that any organism would need to survive. For life to be transported on a rock, it must first survive the violent launch into space. If a massive asteroid or comet crashes into a planet, the impact can send chunks of rock flying into space. But this process involves extreme forces, rapid acceleration, intense shock waves, and sudden temperature spikes. Studies of meteorites from Mars suggest that rocks ejected from a planet can experience pressures between 5 and 55 billion pascals, accelerations of about 3 million meters per second squared, and temperature increases ranging from just 1 degree Kelvin to over 1,000 degrees Kelvin. While these conditions are extreme, some microorganisms have shown an ability to endure such stress. Once in space, microorganisms face another huge challenge: surviving the harsh, airless, radiation-filled environment. Scientists have tested how microbes react to space conditions by exposing them to simulated space environments and even sending them to low Earth orbit. Some bacteria have developed survival mechanisms, such as forming biofilms that provide extra protection against harmful ultraviolet rays. Certain extremophiles, microbes adapted to extreme environments, have demonstrated an incredible ability to endure space-like conditions, making it plausible that life could survive a long journey through space. The final challenge is surviving the descent onto another planet. As the rock falls through the atmosphere, it experiences intense heat due to friction, sometimes reaching temperatures that can destroy any life inside. Scientists have conducted experiments to test whether spores can survive this fiery re-entry. In one experiment, spores of Bacillus subtilis were placed on granite rocks and sent into space aboard a 2-stage Orion rocket. When the rock re-entered Earth's atmosphere, the spores on the sides of the rock survived, but those on the front-facing surface, which reached a temperature of 145 degrees Celsius, did not. This suggests that photosynthetic organisms, which need sunlight and must stay near the surface of a rock, might be less likely to survive atmospheric entry. On the other hand, tiny microbes buried deep inside a rock could be shielded from the worst of the heat and might stand a better chance of making it through. Lithopanspermia is often discussed in the context of planets within the same solar system, such as the possibility of life moving between Earth and Mars. However, some scientists believe the process could also happen on a much larger scale, between different star systems. For instance, researchers have studied the planetary system surrounding the star TRAPPIST-1, which has several Earth-like planets orbiting close together. A recent study suggested that lithopanspermia could be significantly more likely in this system than in the Earth-to-Mars scenario. If true, this means that life could more easily spread between planets in tightly packed planetary systems, potentially increasing the odds of life emerging. Some theories go even further, suggesting that rocky or icy objects traveling between star systems in the Milky Way could carry life across vast distances. A mathematical analysis estimated how many such objects might be captured by planetary systems, leading to the possibility that lithopanspermia could take place across the galaxy. However, for this to happen, the life forms inside these rocks would need to survive an incredibly long journey, potentially millions or even billions of years. At this point, there is no direct evidence that lithopanspermia has actually occurred, either within our solar system or between stars. However, if scientists were to find signs of life on two neighboring planets, such as Mars and Earth, that share a clear biological link, it would strongly suggest that life can indeed spread from one world to another. Until then, the idea remains an exciting but unproven possibility, sparking ongoing research and experiments. The idea of lithopanspermia, the theory that life could have traveled between planets on space rocks, faces a lot of challenges. The conditions required for this to happen are extremely complex, and there is strong evidence suggesting that bacteria would struggle to survive the harsh journey through space. Because of this, many scientists find it hard to support the theory. However, massive asteroid impacts were very common in the early days of our solar system, and even today, collisions still occur, especially within the asteroid belt. A more unusual idea, known as directed panspermia, was introduced in the early 1970s by Francis Crick, a Nobel Prize-winning scientist, along with his colleague Leslie Orgel. This theory suggests that life on Earth did not evolve here by chance, but was instead deliberately placed on our planet by an advanced extraterrestrial civilization. At the time, scientists were skeptical that life could have naturally arrived on Earth through either radiation-driven panspermia or lithopanspermia. Because of this, Crick and Orgel considered the possibility that intelligent beings from another world might have sent life here on purpose. However, Orgel did not take the idea as seriously as Crick. They both admitted that there was no strong scientific proof for their theory, but they discussed what kind of evidence would be needed to support it. A similar, but more light-hearted, theory was proposed by astrophysicist Thomas Gold. He suggested that life on Earth might have come from extraterrestrial cosmic garbage, essentially waste materials accidentally left behind by alien visitors. While these ideas sound like science fiction, Crick and Orgel used a concept called cosmic reversibility to justify their argument. The idea is simple. If human civilization ever reaches the point where we can deliberately introduce life to another planet, what is stopping the possibility that an advanced alien species did the same thing to Earth in the distant past? They believed that, in the near future, humanity might be capable of seeding life on another world in a similar manner. As for actual evidence, Crick and Orgel pointed out that the genetic code of all living organisms on Earth is universal. To them, this suggested that life could have been infected onto our planet in a deliberate manner. They even speculated that if directed panspermia were true, the original alien senders might have embedded a hidden message within the DNA of the first microorganisms that arrived on Earth nearly 4 billion years ago. However, due to natural selection and genetic mutations, any such message would likely have been erased over time, making it nearly impossible to detect today. Back in the early 1970s, both the idea that life originated on Earth, abiogenesis, and the theory that life came from space, panspermia, were considered possible explanations by different scientists. Crick and Orgel pointed out that there was no experimental proof at the time to clearly favor one theory over the other. However, modern scientific discoveries have provided much stronger evidence for abiogenesis, the idea that life developed naturally on Earth, while evidence for panspermia, especially directed panspermia, remains extremely weak. There is another, more widely accepted idea called pseudo-panspermia. This theory suggests that while life itself may not have come from space, many of the basic organic molecules needed for life, such as sugars, amino acids, and the building blocks of DNA, formed in space and later arrived on Earth, possibly through meteorite impacts. Over time, these molecules combined and eventually led to the emergence of life through natural processes. Strong evidence supports this idea, as scientists have found organic compounds in meteorites, comets, and even in space dust. Experiments have also shown that these compounds can form under conditions that mimic those in space. One of the most famous cases involving a possible extraterrestrial life discovery happened in the mid-19th century. On May 14, 1864, a meteorite broke apart in the sky over the French city of Orgueil, raining down about 20 fragments. In 1965, scientists examined one of these fragments, which had been stored in a sealed glass jar since its discovery. To their surprise, they found what appeared to be a seed capsule embedded inside the meteorite, while the outer glassy surface of the rock remained undisturbed. This sparked excitement, as it seemed to be proof that life had come from space. However, further analysis revealed that the seed was actually from a European rush plant, and it had been carefully glued into the rock, with coal dust used to disguise the tampering. The outer fusion layer of the meteorite was actually just glue. The person responsible for the hoax was never identified, but it is believed that they may have been trying to influence the 19th century debate on whether life could spontaneously generate from non-living matter. A more recent and mysterious discovery was made in the year 2017. Astronomers using the Pan-STARRS telescope in Hawaii detected a strange, reddish-colored object measuring up to 400 meters in length. Its unusual orbit suggested that it came from outside our solar system, making it the first confirmed interstellar object ever observed. The scientist, Avi Loeb, proposed that this object could have been an artifact from an alien civilization and might even be evidence supporting directed panspermia. However, most experts consider this idea to be unlikely. For many years, scientists studied Oumuamua, trying to understand what exactly it was. Eventually, most astronomers agreed that it was likely a comet. However, it moved in a way that no other comet had before. The most widely accepted explanation for this strange behavior is that Umuamua might have a layer of frozen hydrogen on its surface. When sunlight hits this hydrogen, it reacts by turning into gas and escaping into space. This not only speeds up Umuamua, but also changes its path as it travels through our solar system. Another clue that supports this theory is its reddish color. This suggests that Umuamua has been bombarded by cosmic rays for a very long time, perhaps millions or even billions of years. Over time, these rays could have helped it accumulate the frozen hydrogen that causes its unusual movements. Even though this is the leading explanation, scientists are not entirely certain. That's why they are considering an ambitious plan to chase after this mysterious visitor. The idea is to send a spacecraft fast enough to catch up with Umuamua, even though it is already far from Earth. The mission, called Project Lyra, would use the gravity of both Earth and Jupiter to slingshot a probe deep into space. This method, known as a gravity assist, would allow the probe to gain enough speed to reach Umuamua. If successful, it would be the fastest spacecraft ever sent into space. The plan is for the probe to launch from Earth, loop around our planet once, then head toward Jupiter. Once near Jupiter, the probe would be pulled in by the planet's gravity and then flung back toward Earth. A second close pass by our planet would give it one final push, sending it hurtling toward Oumuamua at an incredible speed. But Oumuamua is not the only strange object scientists want to study. Project Lyra is also interested in another mysterious space traveler, Borisov. Unlike Oumuamua, which was first spotted by professional astronomers, Borisov was discovered by an amateur stargazer. This comet was first seen in August of the year 2019, and scientists quickly realized that, like Oumuamua, it came from another star system. What makes Borisov particularly interesting is how different it is from anything we've seen before. Its cloud of gas and dust is incredibly smooth, with no visible surface features like the rough, rocky comets in our solar system. When scientists analyzed the light reflecting from Borisov, they found something surprising. It was much cleaner than any comet we've ever observed. This means it has fewer impurities and is made of more pristine materials, possibly unchanged since the early days of its home star system. Another strange discovery was that Borisov was shedding enormous amounts of dust, over 400 pounds every second. It also contained far more carbon monoxide than comets from our solar system typically do. Even more fascinating, the levels of carbon monoxide were not the same everywhere on the comet, suggesting that Borisov may have formed close to its original star before drifting outward due to the gravitational pull of larger planets in its home system. One of the most puzzling things about Borisov is how its light behaves. The way it reflects sunlight is far more polarized than any other comet we've ever studied. This unusual characteristic, combined with its smooth gas cloud, suggests that Borisov has never passed near a star before, not even the one it originally came from. That makes it one of the purest, most untouched objects we've ever seen in space. With so many unanswered questions, scientists hope that by studying both Oumuamua and Borisov, they can unlock new secrets about how comets form, how they travel through space, and perhaps even how solar systems, including our own, came to be. Project Lyra is a research initiative aimed at figuring out whether we could send a spacecraft to study interstellar objects like Umuamua and 2I Borisov. It was launched on the 30th of October, 2017 by the Initiative for Interstellar Studies, also known as I4Eyes. At first, scientists thought Umuamua was moving too fast for any spacecraft to catch up with it. However, in January 2022, researchers suggested that a spacecraft launched from Earth could reach it in about 26 years, making a close-up study possible. Initially, I4Eyes proposed launching a spacecraft in 2021 and estimated it could reach Umuamua within 5 to 10 years. The plan involved a clever use of gravity. First, the spacecraft would swing by Jupiter to gain speed, then dive extremely close to the Sun, within 3 to 10 times the Sun's radius, to take advantage of a phenomenon called the Oberth effect, which would give it an extra boost of speed. Later studies presented new possibilities, suggesting a launch in either 2030 or 2033. These plans used a similar strategy, but included an additional maneuver called the Vinfinity leveraging maneuver in the 2030 option. The total travel time for these missions was estimated at around 22 years. This meant that although the initial launch window had passed, there were still future opportunities to reach Oumuamua. As research continued, I4Eyes explored other trajectory options that did not require the technically difficult close flyby of the Sun. Instead, they focused on a different approach using a Jupiter Oberth maneuver. This alternative strategy would allow missions to launch between 2026 and 2033, depending on the specific route and gravity assists chosen before reaching Jupiter. Additionally, more advanced propulsion methods were considered, including solar sails, laser sails, and nuclear propulsion. These futuristic technologies could provide alternative ways to catch up with fast-moving interstellar objects like Oumuamua. The biggest challenge in reaching Oumuamua is not just getting there quickly, but also slowing down enough to study it properly. If a spacecraft is moving too fast, it would simply fly past the object without being able to enter orbit or land on it. Scientists emphasize that slowing down at the right moment would be highly beneficial, as a high-speed flyby would limit the amount of scientific data that could be gathered. Despite these difficulties, researchers believe a mission to Oumuamua is possible using technology that already exists or is being developed. Astronomers Seligman and Laughlin, who have studied the feasibility of such missions, agree that while they are difficult to carry out, they are both scientifically valuable and achievable. One proposed plan involved launching a spacecraft with a Falcon Heavy-class rocket, carrying a probe weighing only a few dozen kilograms. The spacecraft would use a heat shield similar to the one on the Parker Solar Probe, and would rely on a combination of a Jupiter flyby and a close approach to the Sun to gain enough speed to reach Oumuamua. If launched in 2021, this plan could have worked. However, later research found that other launch windows exist, with the next opportunities coming in 2030 or 2033. These missions would use a solar obverse maneuver at a distance of 6 times the Sun's radius and would take more than 20 years to reach their target. While this may seem like a long time, it is worth noting that the Voyager probes, which launched over 45 years ago, are still functioning to some extent today. More recent studies by the Project Lyra team at I4Eyes have identified additional mission possibilities, including a launch in 2028. This mission would use a Jupiter obverse instead of the more challenging solar obverse maneuver, making it more feasible with current technology. In addition to traditional rocket-based missions, scientists are exploring cutting-edge propulsion methods that could make interstellar travel easier. These include solar and laser electric propulsion, laser sails inspired by the breakthrough Starshot project, and even nuclear propulsion. Such technologies could revolutionize space exploration, making it possible to reach objects like Umuamua much faster than conventional spacecraft. While the initial plans to reach Umuamua in the early 2020s, scientists might be getting closer to finding a massive, icy planet lurking beyond Neptune's orbit. Recent efforts to map the universe using data from a powerful telescope in Hawaii have ruled out nearly 4/5 of the possible locations where this mysterious world could be hiding. Some call it Planet 9, while others prefer Planet X. But whatever the name, this possible planet has been stirring debate since scientists first proposed its existence. The biggest question remains unanswered. Does it actually exist? If discovered, Planet 9 would be the 5th largest planet in our solar system, with a mass estimated to be 10 times that of Earth. Scientists also believe it is mostly made of gas, much like Uranus. The first major study on this potential planet, published in the year 2016, suggested that it orbits the Sun at a staggering distance, 29 times farther than Neptune. Since Neptune itself is about 2,800,000,000 miles from the Sun, that means Planet 9 would be in an incredibly distant and frigid part of space. Because of this vast distance, scientists estimate that a single orbit around the Sun would take anywhere between 10,000 and 20,000 years. If this hidden world is ever confirmed, it would reshape our understanding of the outer solar system and dominate a region larger than any other known planet in our cosmic neighborhood. Imagine a world covered in ice as far as the eye can see, a frozen planet where the surface is made of solid water, methane, ammonia, and other icy substances. These planets, often called ice planets, are incredibly cold and covered in layers of frozen materials, forming what scientists call a global cryosphere, a world trapped in an eternal deep freeze. Under a scientific definition, many small frozen worlds in our solar system qualify as ice planets. Some of the most well-known include Ganymede, Titan, Europa, Enceladus, and Triton, moons of giant planets like Jupiter, Saturn, and Neptune. But icy worlds aren't limited to moons. They also include dwarf planets such as Pluto, Orcus, Haumea, Makemake, Quaoar, Sedna, Gongong, and Eris, as well as the largest known comets. Beyond our solar system, scientists at NASA reported in June of the year 2020 that ice planets and ocean worlds might actually be common in our Milky Way galaxy. Their conclusion was based on complex mathematical models, suggesting that many exoplanets, planets outside our solar system, could have vast oceans hidden beneath thick ice. One of the first possible ice planets discovered outside our solar system was Ogle 2005 BLG 390 LB, spotted in the year 2005. The surface of an ice planet can be composed of different frozen chemicals, depending on how cold it is. If mostly made of water ice, the temperature would be below 260 Kelvin, about -13 degrees Celsius. If carbon dioxide, also known as dry ice, and ammonia are dominant, the temperature would drop below 180 Kelvin, about -93 degrees Celsius. If methane makes up most of the ice, the temperature would plummet even further to below 80 Kelvin, about -193 degrees Celsius. These worlds are some of the coldest places in the universe, with surfaces so frigid that most known life forms would be unable to survive. At first glance, an ice planet seems like the last place where life could exist. Its surface is frozen solid, and the extreme cold makes it nearly impossible for liquid water to exist above ground. However, many of these frozen worlds may have hidden oceans beneath their icy crusts. These underground oceans could be warmed by heat coming from inside the planet or by the gravitational pull of a nearby larger body, like a giant planet. If such oceans exist, they might be home to living creatures. Microorganisms could survive using chemical energy in a process called chemosynthesis, where they break down minerals and chemicals to create food, just like some bacteria do near deep-sea hydrothermal vents on Earth. If conditions are right, some of these oceans might even support more complex organisms like plankton or alien fish. However, since these oceans are buried beneath thick ice, plants as we know them could not grow. They need sunlight for photosynthesis, and no sunlight can reach these hidden waters. That said, some ice worlds might have thick atmospheres, surface lakes, or even seas of liquid chemicals, like Saturn's largest moon, Titan. On Titan, lakes of liquid methane and ethane cover the surface, raising the possibility of life forms very different from anything on Earth. Ice planets may be some of the most common worlds in the universe. While they may seem inhospitable, their hidden oceans make them one of the best places to search for alien life. Scientists continue to study these fascinating frozen worlds, hoping to uncover secrets buried beneath their icy shells. Who knows? One day, we might find that life exists in the cold, dark depths of an ice planet's hidden ocean. Time travel has fascinated humans for centuries, with countless books and movies exploring what it would be like to jump into a futuristic machine and suddenly appear in another era, whether in the distant future or the ancient past. While this remains purely science fiction for now, scientists believe that time travel is theoretically possible. The problem isn't whether it can be done, but rather how to develop the technology needed to make it happen. Time travel, at its core, is about how time passes for different objects in the universe. It's not as fixed as we might think. In fact, time can speed up or slow down, depending on how fast you're moving or how strong the gravitational force is around you. This idea comes from Albert Einstein's famous theories of relativity, which have been tested and confirmed by multiple scientific experiments. So, let's break it down into two main ways time travel could work. One of the most promising ways to travel to the future is by moving at speeds close to that of light. This idea comes from Einstein's theory of special relativity, which states that as an object moves faster, time slows down for it. But we're not talking about driving at high speeds on the highway. This would require speeds so fast that they are almost unimaginable. To test this theory, scientists conducted an experiment using two identical clocks. One clock was placed on an airplane, while the other remained on the ground. After the plane flew around for a while and returned, scientists compared the two clocks. The results were astonishing. The clock on the airplane ticked more slowly than the one on the ground. This happened because the plane was moving at a high speed, proving that time slows down for objects in motion. Now, imagine taking this to the extreme. If we could build a spaceship that traveled at nearly the speed of light, time for the passengers inside would slow down significantly compared to people on Earth. For example, if you spent a year traveling in this super-fast spaceship, decades or even centuries could pass on Earth. When you return, you'd find yourself in the distant future, while you would have only aged a little. This might sound far-fetched, but nature has already given us a glimpse of how this works. Scientists have observed tiny particles called neutrinos, some of which move at speeds close to that of light. At these speeds, 1 second for them is equal to 11 months for us. If humans could somehow travel at similar speeds, we could experience time at an entirely different rate than those left behind. The second way time travel could work is through the power of gravity, a concept explained by Einstein's theory of general relativity. According to this theory, time moves more slowly in areas with stronger gravity. This means that if you are in a place with intense gravitational force, time would slow down for you compared to someone in a place with weaker gravity. To prove this, scientists conducted another experiment with 2 identical clocks, just like before. This time, they placed one clock on a higher shelf and the other on a lower shelf. When they compared the two, they found that the lower clock ticked more slowly because it was closer to the Earth's center, where gravity is stronger. Even though the difference was tiny, it confirmed that gravity does affect time. Now, imagine taking this concept to an extreme level. If you wanted to travel far into the future, you would need to be near a place with an unbelievably strong gravitational force, like a black hole. A black hole is a region in space where gravity is so intense that not even light can escape it. Matter inside a black hole gets squeezed into an incredibly tiny space, creating a gravitational force stronger than anything we experience on Earth. If a person were to orbit close to a black hole without falling in, time would move much more slowly for them compared to someone far away from it. For example, if an astronaut spent a few hours near a black hole, many years could pass for people on Earth. This concept was beautifully illustrated in the movie Interstellar, where the characters landed on a planet close to a black hole. While they spent just a few hours there, decades passed for those on their spaceship waiting far from the black hole. Now, here's something fascinating. The GPS systems in our phones and cars actually have to account for the effects of time dilation to work properly. This is because the satellites they rely on are moving at high speeds and experiencing weaker gravity compared to Earth's surface. If scientists didn't make precise adjustments for these effects, your phone's GPS wouldn't be able to tell you exactly where you are. There's another way to experience time differently, and it has nothing to do with black holes or cosmic forces. Scientists are looking into ways to slow down the body's internal processes, allowing people to skip ahead to the future. This isn't traditional time travel where you move through space and time, but rather a way to slow your body's aging while the outside world continues as normal. Animals like bears and squirrels do something similar during hibernation. They lower their metabolism, needing less food and oxygen to survive. Scientists are exploring whether humans can achieve the same effect, even if only for a few hours at a time. This could be incredibly useful in medical emergencies, allowing doctors to put a patient into a temporary hibernation until they can reach proper treatment. In the year 2005, researchers successfully slowed down the metabolism of mice by exposing them to a special gas. However, when they tried this with larger animals, it didn't work as well. Another mind-blowing possibility for time travel involves something called wormholes. Imagine placing 2 balls on a stretched-out trampoline. Normally, they stay apart, unable to touch. But if you press down in the middle, the fabric bends, bringing the balls closer together. Now, think of space as that fabric, and stars as the objects pressing down on it. A wormhole is like a tunnel that forms between 2 distant points, potentially allowing for rapid travel across vast distances, or even through time itself. Some scientists, including the late Stephen Hawking, believe that wormholes might constantly appear and disappear at microscopic scales, smaller than an atom. The challenge is figuring out how to capture and expand one large enough for humans to travel through. But even if we could find a stable wormhole, there's another problem. The slightest extra weight, like that of a human body, might cause it to collapse instantly, snapping shut like an overstretched rubber band. An American physicist named Ron Mallett has a different idea. He believes that time travel could be possible using light. His theory involves creating a swirling cylinder of laser beams. If an object were placed inside this rotating structure, it might be moved through both space and time. similar to how a bubble swirls in a cup of coffee when stirred. Mallet has been working to raise funds to test his theory by dropping tiny particles called neutrons through a ring of spinning lasers. However, many scientists argue that his idea is flawed and doesn't need further testing. Even if we could travel through time, there's a major issue to consider. What happens if someone changes the past? This is known as the time travel paradox. One of the most famous examples is the grandfather paradox, where someone goes back in time and prevents their own grandfather from having children. If that were to happen, how could they exist in the present at all? But recent research from the University of Queensland suggests this may not be a real problem. Scientists have done calculations showing that even if something in the past was changed, time would somehow correct itself, keeping events on track. In other words, no matter what you do, history might always find a way to unfold as it was meant to. Unless, of course, you manage to harness 1.21 gigawatts of power, jump into a DeLorean, and make like Marty McFly. While these theories suggest that traveling to the future is possible, the real challenge is traveling back to the past. Unlike slowing down time, which has been proven, there is no solid evidence that time can be reversed. Some theories suggest that wormholes, hypothetical tunnels in space that connect different points in time, could make it possible to travel to the past. However, there is no proof that wormholes even exist, let alone that they could be used for time travel. Even if time travel to the future is possible, there are enormous challenges to overcome. Speed limitations. The fastest speed humans have achieved so far is far below what would be needed for significant time travel. Extreme gravity conditions. Getting close to a black hole without being destroyed is nearly impossible with current technology. Lack of a way back. Even if we travel to the future, there is no confirmed way to return to the present or past. These are certainly fascinating ideas, but there isn't a single piece of direct evidence or an actual observation to prove them yet. However, before dismissing this as pure speculation, it's important to understand that the researchers behind these claims didn't just make wild guesses. They used advanced mathematical models and powerful computer simulations to predict what this mysterious planet might be like, because that's what scientists do. The idea of this hidden planet is intriguing because it could help explain some unusual patterns observed far beyond Neptune. Specifically, we're talking about the Kuiper belt, a massive, ring-shaped region of space filled with icy remnants from the early days of our solar system. This belt contains countless frozen objects, including comets and small planets like Pluto. Now, here's where things get really strange. The 6 most distant objects in the Kuiper belt all have elongated orbits that are mysteriously aligned in the same direction. Even more puzzling, their orbits are tilted about 30 degrees downward compared to the flat plane where the 8 known planets orbit the Sun. What makes this even more bizarre is that despite moving at different speeds through space, these objects maintain this unusual alignment. The odds of this happening by pure chance are incredibly low, only about 7 in 10,000. That's where the idea of Planet 9 comes in. Scientists propose that this enormous, unseen world could be lurking in the outer reaches of the solar system, exerting a powerful gravitational pull that subtly shapes the orbits of these distant objects. If it exists, it could be the missing piece of the puzzle explaining this cosmic mystery. The Kuiper belt is a vast, icy region located at the edge of our solar system, starting just beyond the orbit of Neptune. This belt stretches from about 30 times the distance between the Earth and the Sun to around 50 times that distance. Although it is similar to the asteroid belt found between Mars and Jupiter, the Kuiper belt is much larger, about 20 times wider and containing up to 200 times more material. However, unlike the rocky and metallic asteroids of the inner solar system, most of the objects in the Kuiper belt are made of frozen substances like methane, ammonia, and water ice. This distant region is home to several dwarf planets, including Pluto, Haumea, Makemake, Quaoar and Orcus. Some of the moons orbiting planets in our solar system, like Neptune's Triton and Saturn's Phoebe, might have originally come from this icy belt. The Kuiper belt is named after Gerard Kuiper, a Dutch astronomer who suggested its existence in 1951. However, he was not the first or the only scientist to propose the idea of a distant belt of small, icy bodies. In the 1930s, Kenneth Edgeworth speculated about a similar region beyond Neptune. Later, in 1980, Julio Angel Fernandez wrote a paper suggesting that a belt of comets beyond Neptune could explain the source of short-period comets, comets that take less than 200 years to orbit the Sun. For a long time, the only known object in this region was Pluto, discovered in 1930, followed by its moon Charon, found in 1978. It wasn't until 1992 that astronomers discovered another object in the Kuiper belt, a small body named Albion. Since then, scientists have identified thousands of Kuiper belt objects, KBOs, and they estimate that more than 100,000 of these icy bodies, each at least 100 kilometers, about 62 miles wide, are still waiting to be discovered. Initially, astronomers believed that short-period comets, which orbit the Sun in less than 200 years, came from the Kuiper belt. However, later research showed that most of these comets actually come from a nearby, more chaotic region called the scattered disk, which formed about 4.5 billion years ago due to Neptune's gravitational influence. Some objects from this region, such as Eris, have extreme orbits that take them up to 100 times the distance from Earth to the Sun. The Kuiper belt is often confused with the Oort cloud, another distant collection of icy objects. However, the Oort cloud is believed to be much farther away, about 1,000 times more distant, and forms a nearly spherical shell around the solar system. Both the Kuiper belt and the Oort cloud are part of a larger group of objects known as trans-Neptunian objects, TNOs, which orbit the Sun beyond Neptune. Among the many objects in the Kuiper belt, Pluto is the largest and most well-known. However, Pluto's discovery led to debates about whether it should still be classified as a planet. As scientists found more objects similar to Pluto in the Kuiper belt, they realized that Pluto was just one of many such bodies. In 2006, this led to Pluto being reclassified as a dwarf planet instead of a full-fledged planet. Pluto belongs to a special group of Kuiper belt objects called Plutinos, which share a unique orbital pattern, known as a 2-to-3 resonance with Neptune, meaning they complete 2 orbits around the Sun for every 3 Neptune completes. Scientists often use the Kuiper belt and Neptune as a rough boundary for the solar system. Some prefer to define the edge of the solar system by the heliopause, the region where the Sun's influence fades, or by the distance where the gravitational pull of other stars becomes stronger than the Sun's. After Pluto's discovery in 1930, astronomers started wondering if other objects existed in the same region. Frederick Leonard, an astronomer, was one of the first to suggest that Pluto might be part of a larger family of ultra-Neptunian bodies waiting to be discovered. Around the same time, another astronomer, Armin Leuschner, speculated that Pluto could be just one of many yet-to-be-found planetary objects in the distant solar system. In 1943, Kenneth Edgeworth proposed that beyond Neptune, the material left over from the formation of the solar system was too spread out to form full-sized planets. Instead, he believed it had formed a vast collection of smaller objects. He also suggested that some of these objects could be knocked out of their orbits and travel toward the inner solar system, becoming comets. In 1951, Gerard Kuiper published a paper proposing that a disk of icy remnants had formed in the early solar system. He described how frozen materials, including water, ammonia, and methane, gathered to form small celestial bodies. According to his theory, these objects could have scattered comets across the solar system, with Pluto playing a major role in this process. At the time, Kuiper and many others believed that Pluto was the same size as Earth, which made his theory more plausible. However, we now know Pluto is much smaller, and Kuiper's original idea had some flaws. The idea of a distant icy belt continued to evolve throughout the 20th century. In 1962, physicist Al Cameron suggested that the solar system's outer edges contained an enormous amount of small material. Then, in 1964, Fred Whipple, the scientist famous for his dirty snowball theory of comets, proposed that a comet belt might explain oddities in the orbit of Uranus. However, further observations ruled out this specific idea. For decades, the Kuiper belt was nothing more than speculation. It wasn't until 1992 that the first direct evidence was found, confirming the existence of this vast, icy region at the edge of our solar system. In the year 1977, astronomer Charles Cowell made a groundbreaking discovery when he found an icy celestial body known as 2060 Chiron. This small planetoid orbits between Saturn and Uranus, making it an unusual find. To spot it, Cowell used a special device called a blink comparator, the same tool that had helped Clyde Tombaugh discover Pluto nearly 5 decades earlier. 15 years later, in 1992, astronomers found another similar object, named 5145 Pholus, which shared a similar orbital path. Over time, more and more of these mysterious objects were discovered, leading scientists to classify them as a distinct group called the Centaurs. These celestial bodies, found between Jupiter and Neptune, behave like comets, but their orbits are highly unstable. Because of this instability, their lifespans in the solar system are only a few million years. Since the discovery of Chiron, astronomers have wondered how these centaurs continue to exist. If they are disappearing over time, there must be a source replenishing them. Additional clues about the existence of a vast hidden region in space came from studying comets. Scientists had long known that comets do not last forever. As they travel closer to the Sun, its intense heat causes their icy surfaces to turn into gas, gradually making them disappear. Yet, comets have been observed throughout history, meaning there must be a way for new ones to replace those that vanish. One possible explanation was proposed in 1950 by Dutch astronomer Jan Oort. He theorized that a giant, spherical cloud of icy objects, later called the Oort cloud, exists far beyond the solar system, stretching more than 50,000 times the distance from Earth to the Sun. According to this theory, this distant reservoir is the birthplace of long-period comets, such as the famous Hale-Bopp, which can take thousands of years to complete an orbit around the Sun. But astronomers knew there was another type of comet, short-period comets, such as Halley's Comet, which return in less than 200 years. By the 1970s, scientists began noticing a problem. There were too many short-period comets for them to have come only from the Oort cloud. For one of these distant objects to become a short-period comet, it would need to be captured by the gravitational pull of the giant planets, a process that seemed unlikely to explain the sheer number of these comets. In the year 1980, Uruguayan astronomer Julio Fernandez published a study in the monthly notices of the Royal Astronomical Society, proposing a new idea. He calculated that if the Oort cloud were the sole source of short-period comets, then for every one comet that made it into the inner solar system, about 600 others would have been ejected into deep space, something that did not match observations. Fernandez suggested that a belt of icy bodies must exist somewhere between 35 and 50 times Earth's distance from the Sun. Building on Fernandez's theory, a team of Canadian scientists, Martin Duncan, Tom Quinn, and Scott Tremaine, used computer simulations in 1988 to test whether the Oort cloud alone could explain all known short-period comets. Their results showed that the Oort cloud could not be the only source because short-period comets tend to appear near the plane of the solar system, while Oort cloud comets can come from any direction in the sky. When the scientists added the idea of a belt of objects into their calculations, everything suddenly made sense. Because the words Kuiper and comet belt appeared in the opening of Fernandez's research paper, Tremaine decided to name this hypothetical region the Kuiper Belt. Meanwhile, another astronomer, David Jewett, was growing increasingly curious about what lay beyond Pluto. In 1987, while working at the Massachusetts Institute of Technology, he became fascinated by what he called the emptiness of the outer solar system. He recruited graduate student Jane Liu to help search for objects beyond Pluto, telling her, "If we don't look, no one will." Jewett and Liu used the same method that Clyde Tombaugh and Charles Cowell had used, scanning the night sky with a blink comparator. At first, the process was painstakingly slow. Each pair of photographic plates took about 8 hours to examine. However, the arrival of a new technology, charge-coupled devices, CCDs, revolutionized their work. Unlike traditional photography, CCDs could capture 90% of the light that hit them, compared to just 10% for photographic plates. This allowed astronomers to search the skies much more efficiently, speeding up the process dramatically. In 1988, Jewett moved to the University of Hawaii's Institute for Astronomy, and Liu later joined him. Working at the university's 2.24-meter telescope atop Mauna Kea, they continued their search with improved CCD cameras. Over time, CCD technology advanced, allowing them to cover larger areas of the sky much faster. Finally, after 5 years of searching, their patience paid off. On August 30th, 1992, Jewett and Liu announced the discovery of a mysterious new object, 1992 QB1. This was the first direct evidence of a body belonging to the long-hypothesized Kuiper Belt. This object was later given the official name 15,760 Albion. Just 6 months later, they discovered another Kuiper Belt object, named 181,708 1993 FW. As astronomers continued their observations, they discovered more and more objects in the Kuiper Belt. By the year 2018, over 2,000 of these icy bodies had been identified. Within the first 20 years after the discovery of 1992 QB1, more than 1,000 objects had been found, proving that Pluto was not alone, but part of a vast region of frozen worlds. Even in the 2010s, much about the Kuiper Belt remained a mystery. However, new insights came with the arrival of the spacecraft New Horizons. Launched to study Pluto, New Horizons became the first spacecraft to fly by a Kuiper Belt object up close. In the year 2015, it sent back stunning images of Pluto and its moons, revealing an unexpectedly dynamic world. Then, in the year 2019, New Horizons performed another flyby, this time of a distant Kuiper Belt object named Arakoth. This provided scientists with an even closer look at the icy remnants from the formation of the solar system. Since scientists first started mapping the region beyond Neptune, they've discovered that the Kuiper Belt isn't the true birthplace of short-period comets. Instead, these comets come from a related region called the scattered disk. The scattered disk formed long ago when Neptune moved outward from the Sun, disrupting a much closer version of the Kuiper Belt. This movement left behind two groups of objects, one that remained stable and mostly untouched by Neptune's gravitational pull, the Kuiper Belt we know today, and another with orbits still influenced by Neptune, the scattered disk. Because the scattered disk is still active while the Kuiper Belt is relatively calm, astronomers now believe most short-period comets originate from the scattered disk. Sometimes the Kuiper Belt is called the Edgeworth Kuiper Belt to credit the astronomer Edgeworth, and its objects, KBOs, are sometimes referred to as echos. However, some experts argue that neither Edgeworth nor Kuiper fully predicted what we now see in this region. Astronomer Brian G. Marsden believes that Fred Whipple was actually the closest to getting it right, while David Jewett suggests that Julio Fernandez deserves credit for correctly predicting the Kuiper Belt. KBOs are occasionally called Kuiperoids, a term suggested by astronomer Clyde Tombaugh. However, many scientists prefer the term trans-Neptunian objects, TNOs, because it avoids controversy. But it's important to note that while all KBOs are TNOs, not all TNOs are KBOs. The term TNO applies to any object orbiting the Sun beyond Neptune, including those in the scattered disk. The Kuiper belt, not counting the scattered disk, spans a vast distance from about 30 to 55 times the distance between the Earth and the Sun, astronomical units. Its main region stretches from around 39.5 to 48 astronomical units. Instead of a flat belt, it's more like a thick torus, or donut-shaped ring, with objects scattered well above and below the plane of the solar system. Some objects in the belt extend 10 degrees above or below this plane, while others are even farther out. On average, the belt is tilted about 1.86 degrees compared to the plane of the solar system. Neptune plays a crucial role in shaping the Kuiper belt's structure. Over billions of years, its gravity has destabilized the orbits of objects in certain areas, pushing some into the inner solar system, some into interstellar space, and others into the scattered disk. This gravitational influence has created noticeable gaps in the Kuiper belt, similar to the empty spaces in the asteroid belt known as the Kirkwood gaps. For instance, in the region between 40 and 42 astronomical units, no objects can maintain stable orbits for long periods. Any objects found there must have drifted in fairly recently. Between the key gravitational zones of Neptune, called the 2 to 3 and 1 to 2 resonances, there's a region from about 42 to 48 astronomical units where objects remain stable over long timescales. This area is known as the classical Kuiper belt, and it contains about 2/3 of all observed KBOs. The first KBO discovered in modern times was named Albion, originally called Object 15760 1992 QB1, and it became the model for this group. Because of this, classical KBOs are sometimes nicknamed Kubewanos, a playful reference to the letters in its original name. The International Astronomical Union requires that classical KBOs be named after mythological figures linked to creation. Scientists believe the classical Kuiper belt is actually made up of two distinct groups. The first, called the dynamically cold population, consists of objects that move in nearly circular orbits with very little tilt, similar to the planets. Their orbits have an eccentricity of less than 0.1, meaning they don't stray far from their expected paths, and they stay within about 10 degrees of the solar system's plane. Within this cold population, there's a cluster of objects with semi-major axes between 44 and 44.5 astronomical units, known as the kernel. The second group, the dynamically hot population, follows much more tilted and eccentric orbits, some up to 30 degrees from the plane of the solar system. These two groups aren't called hot and cold because of temperature differences, but rather as an analogy to gas particles, where hot particles move more chaotically. However, the differences between these groups go beyond just their orbits. The cold population tends to be redder in color, brighter, and more likely to exist in binary pairs. It also has a different size distribution and lacks the very large objects found in the hot population. Interestingly, the total mass of the dynamically cold population is about 30 times less than that of the hot population. These differences suggest that the two populations may have formed in different parts of the solar system. Scientists believe the hot population originally formed near Neptune's old orbit and was later scattered outward when Neptune migrated. The cold population, however, may have formed in its current location since its loose binary objects likely wouldn't have survived close encounters with Neptune. While the NICE model, a popular theory of planetary migration, helps explain some of these differences, it's also possible that the color variations result from changes in surface composition over time. When an object's orbit follows a specific pattern in relation to Neptune's orbit, something called a mean motion resonance, it can end up in a synchronized dance with Neptune. This means that instead of being thrown off course by Neptune's gravity, the object stays in a stable path as long as their movements stay in sync. For example, imagine an object that orbits the Sun 2 times while Neptune completes 3 orbits. If this object reaches its closest point to the Sun, when Neptune is about 1/4 of an orbit away, then every time it returns to that same spot, Neptune will also be in almost the same place. This happens because Neptune will have completed 1.5 orbits in the same time. This type of orbital relationship is called the 2-to-3 resonance, also written as 3-to-2. And objects in this group move along paths that extend about 39 astronomical units from the Sun. Astronomers have found around 200 objects in this category, including Pluto and its moons. Because Pluto is the most well-known member, these objects are called Plutinos. Even though many Plutinos have orbits that cross Neptune's path, they never actually crash into the planet. Their synchronized movements ensure that they always avoid collisions. However, these objects have very stretched out orbits, meaning they don't follow perfect circles. This suggests that they weren't originally in their current positions, but were instead pushed into them by Neptune as it slowly moved outward from the Sun. The International Astronomical Union, IAU, the organization that names celestial objects, has a rule that all Plutinos must be named after gods and goddesses from underworld mythology, just like Pluto. There is another type of resonance where an object completes just half an orbit, while Neptune completes one full orbit. This is known as the 1-to-2 resonance and corresponds to a distance of about 48 astronomical units from the Sun. However, far fewer objects have been found in this category, and those that do exist are sometimes called Tutinos. There are also other resonances, such as 3-to-4, 3-to-5, 4-to-7, and 2-to-5. Aside from these resonant objects, Neptune also has a group of celestial bodies called Trojans. These objects stay in stable positions ahead of or behind Neptune as it orbits the Sun. They follow a special 1-to-1 resonance, meaning they complete an orbit in the same time as Neptune, but their positions remain balanced by gravity, keeping them safely in place. Interestingly, there is a noticeable lack of objects in certain regions of space where astronomers would expect to find them. One idea to explain this is that as Neptune slowly drifted away from the Sun, its gravitational influence swept through these areas, either capturing objects into resonance or flinging them away. One particularly puzzling feature of the Kuiper belt is what astronomers call the Kuiper cliff. Observations show that beyond a distance of 50 astronomical units, the number of large objects drops off sharply. Scientists had expected to find many more bodies beyond this point, based on estimates of how much material would have been needed to form planets like Uranus and Neptune. However, studies confirm that this decline is real and not just a result of missing observations. There are several possible explanations for the Kuiper cliff. Some scientists believe that there simply wasn't enough material that far out for large objects to form. Others suggest that something may have removed or destroyed many of these objects over time. One researcher, Patrick Likauka from Kobe University, even proposed that an undiscovered planet, possibly the size of Mars or Earth, could be responsible for the mysterious disappearance of objects beyond this point. More recent data collected before September 2023 has shown that the pattern of objects at the edge of the Kuiper belt is similar to the way asteroids are distributed in the outer part of the main asteroid belt between Mars and Jupiter. In both cases, there are noticeable gaps that seem to be influenced by gravitational interactions with large planets. The origins of the Kuiper belt and its strange structure remain a mystery. However, astronomers are eagerly awaiting results from advanced survey telescopes such as Pan-STARRS and the upcoming Legacy Survey of Space and Time, LSST, which are expected to reveal many more unknown objects. The first Pan-STARRS telescope completed its main mission in 2014, and in 2019 its full dataset was made publicly available, helping scientists identify many more Kuiper belt objects. The Kuiper belt itself is believed to be made up of planetesimals, small celestial bodies that formed in the early days of the solar system. These objects are remnants of the original cloud of dust and gas that surrounded the young Sun. Instead of merging into planets, they remained as smaller bodies, with the largest of them, such as Pluto, measuring just under 3,000 kilometers across. Surprisingly, when scientists examined the surface of Pluto and its moon Charon, they found fewer small impact craters than expected. This suggests that many Kuiper belt objects formed directly as larger chunks rather than slowly growing from tiny pebbles over time. One possible explanation is that swirling clouds of small particles clumped together due to gravity, collapsing into larger bodies rather than slowly accumulating piece by piece. Some of these collapsing clouds may have also broken apart, forming binary systems, pairs of objects that orbit each other rather than a single solitary body. Although much progress has been made in studying the Kuiper belt, many questions remain. As new discoveries are made, astronomers hope to gain a clearer understanding of how this distant region of our solar system came to be and what secrets it may still be hiding. Modern computer models suggest that the Kuiper belt, an icy region beyond Neptune, was heavily influenced by the gravitational forces of Jupiter and Neptune. These simulations also reveal that Uranus and Neptune could not have originally formed where they are now. The reason? There simply wasn't enough raw material in that distant part of the solar system to create planets of their enormous size. Instead, scientists believe these ice giants were born much closer to Jupiter, in a region where more material was available. In the early days of the solar system, countless small space rocks called planetesimals were scattered in all directions. This chaotic movement affected the giant planets' orbits. Over time, Saturn, Uranus, and Neptune gradually drifted outward, while Jupiter moved inward. This shifting continued until Jupiter and Saturn entered a special kind of orbital relationship called a 1-to-2 resonance, meaning Jupiter completed 2 orbits around the Sun for every 1 orbit of Saturn. This resonance caused a major gravitational shakeup, destabilizing Uranus and Neptune's orbits and pushing them farther into space. As they moved outward, these 2 planets disrupted the original Kuiper belt, sending some objects flying into deep space and trapping others in new orbits. During this period, Neptune's orbit became highly elongated, and its gravitational influence caused the orbits of many Kuiper belt objects to become unpredictable. Some of these icy bodies drifted outward, forming what scientists now call the cold region of the Kuiper belt, a zone where objects have relatively stable and flat orbits. As Neptune settled into its current position, its orbit became more circular, and many of these scattered objects were captured into resonances, meaning they became locked into predictable orbits that align with Neptune's gravitational pull. Other objects were kicked onto higher inclination paths or ejected completely from the solar system. Many of these ejected planetesimals either became Jupiter Trojans, asteroids that share Jupiter's orbit, irregular moons of the giant planets, or outer belt asteroids. However, the vast majority, more than 99%, were flung out of the solar system entirely. One of the most widely accepted models explaining this planetary movement is called the Nice model, named after the city of Nice in France, where it was developed. This model successfully explains many of the Kuiper belt's features, including the presence of both a cold and hot population of objects, scattered disk objects, and those locked in resonances with Neptune. However, the model is not perfect. For example, it predicts that classical Kuiper belt objects should have more elongated orbits than what we actually observe. It also underestimates the number of objects with highly tilted orbits. Another problem is the existence of binary objects, pairs of Kuiper belt objects that orbit each other at great distances. According to the model, these loose pairs should have been broken apart by Neptune's gravitational influence, yet many remain intact. To address these issues, an updated version of the Nice model suggests that our solar system may have started with 5 giant planets instead of 4. This hypothetical 5th planet was likely another ice giant, similar to Uranus and Neptune. In this revised scenario, all 5 giant planets originally orbited in a tight, orderly chain of resonances. But about 400 million years after the solar system formed, this delicate arrangement collapsed. Rather than being absorbed into the Kuiper belt, The extra ice giant was pushed outward by the gravitational influence of Saturn. It then had a close encounter with Jupiter, which hurled it onto an unstable path. After a series of interactions, this rogue planet was ultimately ejected from the solar system entirely, leaving behind only the 4 giant planets we know today. As Neptune moved outward, it swept up countless objects into gravitational resonances, creating the structure of the Kuiper belt we see today. Some of these objects settled into stable orbits, forming the hot classical belt, which consists of objects with more tilted and irregular orbits. Scientists estimate that Neptune originally migrated from a distance of 24 astronomical units to its current position at 30 astronomical units over a period of 30 million years. At some point during this migration, Neptune had a gravitational encounter with the now lost ice giant, causing its orbit to shift outward rapidly. This sudden jump left a cluster of objects behind in a specific region of the Kuiper belt, about 44 astronomical units from the Sun. These objects include a unique group of loosely bound blue binary pairs, which likely formed closer to the Sun but were later displaced. If Neptune's orbit remained relatively stable during this encounter, it would have prevented the chaotic scattering of Kuiper belt objects predicted by the original Nice model. Over time, Neptune's slow outward movement continued to shape the Kuiper belt, gradually removing objects with highly elongated orbits and leaving behind a more structured belt. Because Kuiper belt objects are so far from the Sun and other major planets, they have remained largely unchanged since the early days of the solar system. This makes them incredibly valuable to scientists. Studying their composition could provide crucial clues about what the solar system was like when it first formed. However, analyzing these distant objects is extremely difficult. They are small, faint, and billions of miles away. Astronomers rely on spectroscopy, a technique that breaks down light into its individual colors to determine their chemical makeup. When an object's light is analyzed this way, certain substances within it absorb specific wavelengths, creating dark lines in the spectrum. By identifying these unique absorption patterns, scientists can figure out what materials make up these ancient remnants of our cosmic past. The Kuiper belt is a vast region of space beyond Neptune, filled with icy objects, remnants from the early solar system. Scientists have studied these objects and discovered that they are made of a combination of rock and various frozen substances, including water, methane, and ammonia. Because the Kuiper belt is so far from the Sun, temperatures are extremely low, around 50 degrees above absolute zero. This means that many materials that would be gases near the Sun remain frozen solid in this distant region. Since only a few Kuiper belt objects, KBOs, have been measured in detail, scientists know the densities and compositions of only a handful. The size of these objects can be determined in several ways. Telescopes with high-resolution imaging, like the Hubble Space Telescope, can capture their dimensions. Another method involves observing how long an object blocks a star's light when it passes in front of it. Scientists can also estimate size based on the amount of infrared radiation an object gives off, which helps calculate how much sunlight it reflects. Determining an object's mass is even more difficult. This is usually done by studying the orbits of moons around KBOs, but this method only works for a few binary systems. The density of KBOs varies widely, ranging from less than 0.4 to 2.6 grams per cubic centimeter. The least dense objects are thought to be mostly ice with empty spaces inside, making them porous. The densest objects likely contain more rock, with only a thin layer of ice on the surface. Interestingly, smaller objects tend to have lower densities, while the largest ones are much denser. One possible explanation for this is that when large objects formed, they might have lost some of their icy outer layers in collisions with other bodies. In the beginning, astronomers couldn't analyze KBOs in detail and could only observe their basic characteristics, such as color. When they did, they found something surprising. These objects weren't all the same shade, but ranged from gray to deep red. Scientists originally expected KBOs to be uniformly dark because cosmic radiation should have stripped away volatile ices from their surfaces. The unexpected variety led researchers to propose different explanations, such as impacts that exposed fresh material or gases escaping from beneath the surface. In 2001, scientists David Jewett and Jane Liu studied KBOs using spectral analysis and found that the color differences were too extreme to be random. The sun's radiation is believed to change the chemistry of methane ice on KBOs, creating complex organic substances known as tholins, which can give objects a reddish hue. Makemake, one of the largest KBOs, has been found to contain hydrocarbons such as ethane, ethylene, and acetylene, which likely formed as radiation broke down methane on its surface. Although most KBOs appear featureless when viewed from Earth due to their faintness, scientists have made progress in identifying their composition. In 1996, astronomer Robert H. Brown and his team studied the object 1993 SC and discovered that its surface is strikingly similar to that of Pluto and Neptune's moon Triton, with large amounts of methane ice. For smaller KBOs, scientists have mainly determined their colors and how much sunlight they reflect. These objects tend to fall into two categories. Some are gray with dark surfaces, while others are bright red with more reflective surfaces. Researchers suspect that this difference may be due to the presence or absence of a chemical called hydrogen sulfide. Objects that formed far from the sun held onto this compound, which, when exposed to radiation, turns their surfaces red. The largest KBOs, such as Pluto and Quaoar, have surfaces containing volatile substances like methane, nitrogen, and carbon monoxide. These chemicals can sometimes turn into gas and escape, only to later freeze and fall back onto the surface like snow. Whether these compounds remain on a KBO depends on how strong its gravity is and how cold it is. Water ice has also been detected on several KBOs, including members of the Oumuamua family, such as 1996-266, as well as medium-sized objects like 38628 Huya and 20,000 Varuna. Some KBOs, like 50,000 Quaoar, even show signs of ammonia hydrate, which suggests that these objects may have experienced past geological activity, with ammonia lowering the melting point of ice and allowing internal movement. Despite its vast size, the Kuiper belt's total mass is surprisingly low. The group of KBOs that move in more chaotic orbits, known as the dynamically hot population, contains only about 1% of Earth's mass. The more stable group, called the dynamically cold population, is even smaller, making up just 0.03% of Earth's mass. Scientists believe that the dynamically hot population once contained far more material but was scattered outward as the giant planets migrated. In contrast, the dynamically cold population may have formed in its current location and never contained much mass to begin with. The most recent estimate, made in 2018, suggests that the entire Kuiper belt weighs just under 2% of Earth's mass, based on the gravitational pull it exerts on planets. The unexpectedly low mass of the dynamically cold population poses a challenge to current models of how the solar system formed. For large KBOs to form through the gradual merging of smaller bodies, there should have been much more material present in the past. However, removing a significant amount of mass from the cold population is difficult to explain. Neptune's gravitational influence isn't strong enough to have swept away that much material, and the idea that collisions gradually ground down large objects into dust doesn't hold up, since many KBOs are loosely bound binary systems that would have been easily destroyed in such a process. Instead, some scientists propose that the largest KBOs may have formed not through collisions, but through a more direct process, where clouds of small particles collapsed into planetesimals without first forming tiny building blocks. The distribution of KBO sizes follows a mathematical pattern known as a power law. This means that as objects get smaller, their numbers increase exponentially. The relationship between size and abundance helps scientists understand the history of the Kuiper belt and how its objects evolved over time. Scientists have recently discovered fascinating differences in the size patterns of objects in the Kuiper belt, a distant region of icy bodies beyond Neptune. These objects are divided into two main groups, the hot classical and cold classical objects. It turns out that the way their sizes are distributed follows different trends. For the hot classical objects, the pattern changes at a size of 110 kilometers. Above this size, the number of large objects decreases at a rate of about 5 times faster, while smaller ones decrease at a slower rate of about 2 times. On the other hand, the cold classical objects show an even steeper decline, 8 times faster for large objects and nearly 3 times for smaller ones, with the shift occurring at 140 kilometers. Interestingly, other groups of Kuiper belt objects, such as scattering objects, Plutinos, and Neptune Trojans, follow a similar trend to the dynamically hot populations. However, instead of a gradual decline, they seem to have a sudden drop in numbers below a certain size. Scientists think this drop could be due to collisions breaking apart larger objects over time, or that these populations originally formed without smaller objects, with the tiny ones we see today being just fragments of bigger bodies. The tiniest known Kuiper belt objects, which are less than 1 kilometer wide, are far too dim for even powerful telescopes like Hubble to see directly. Instead, astronomers have detected them through an interesting method called stellar occultation, where these small objects briefly block the light of a distant star. The first such discovery was made in December 2009 by a team led by astronomer Hilke Schlichting. They found a tiny Kuiper belt object by examining old Hubble Space Telescope data from March 2007. This object, just over 1,040 meters across, was noticed when it briefly blocked a star for only 0.3 of a second. A few years later, in December 2012, Schlichting and her team conducted a deeper analysis of Hubble's archival data and spotted another similar-sized object, slightly larger at about 1,060 meters across. These detections helped scientists calculate how common such small objects are in the Kuiper belt. Their study suggested that objects below 1 kilometer in size are far less common than expected based on the population of larger objects, which are mostly over 90 kilometers wide. NASA's New Horizons spacecraft, which explored Pluto, carried an instrument called the Venetia-Burney Student Dust Counter. This instrument detected much more space dust than scientists had predicted, even as far out as 55 times the distance from the Sun to Earth. This unexpected dust suggests that there might be more small, unseen objects in the outer solar system than previously thought. Beyond the Kuiper belt lies an even more distant and chaotic region called the scattered disk. Unlike the Kuiper belt, where objects have more stable orbits, the scattered disk is home to icy bodies with highly stretched out orbits that often tilt at extreme angles. Most scientific models suggest that both Kuiper belt and scattered disk objects originally formed in a single massive belt of material. Later, gravitational interactions, especially with Neptune, caused some of these objects to be pushed outward into the scattered disk, where their orbits became unstable. Many of the solar system's short-period comets are believed to have originated from this region. Some of these objects drift inward, first becoming centaurs, which orbit between Jupiter and Neptune, before eventually turning into comets that pass close to the Sun. The official definition of a Kuiper belt object, KBO, is an object that orbits entirely within the region of the Kuiper belt, regardless of what it is made of or where it originally came from. Objects that move beyond this belt are classified as scattered disk objects. However, some scientists use the term Kuiper belt object more loosely, applying it to any icy minor planet in the outer solar system, even if it has spent much of its history outside the Kuiper belt. This has led to some confusion, especially with objects like Eris, which is technically a scattered disk object but is often still called a KBO. Another fascinating mystery of the Kuiper belt is Triton, Neptune's largest moon. Unlike other major moons in the solar system, which orbit in the same direction as their planet's rotation, Triton moves in the opposite direction. This unusual behavior suggests that Triton was not originally formed around Neptune, but was instead captured from the Kuiper belt. Capturing a large body like Triton is no easy feat. For Neptune to have grabbed it, something must have slowed Triton down enough for the planet's gravity to take hold. One likely explanation is that Triton was once part of a binary system, a pair of objects orbiting each other. When it passed near Neptune, its companion may have been ejected, while Triton was pulled into orbit around the giant planet. Triton is only about 14% larger than Pluto, and scientists have found that both worlds have similar surface materials, including frozen methane and carbon monoxide. These clues strongly suggest that Triton was once a Kuiper belt object before Neptune's gravity captured it. For more than 2 decades, astronomers have been discovering large objects in the Kuiper belt, an icy region beyond Neptune filled with countless celestial bodies. Since the year 2000, several Kuiper belt objects, KBOs, have been found with diameters ranging between 500 kilometers and 1,500 kilometers. To put that into perspective, Pluto itself has a diameter of approximately 2,370 kilometers, meaning these newfound KBOs are more than half its size. One of the first major discoveries was Quaoar in the year 2002. This object measures over 1,200 kilometers across. Even larger KBOs followed, including Makemake and Haumea, which were both officially announced on the 29th of July in the year 2005. Other sizable discoveries include the object named Ixion, found in the year 2001, and Varuna, which was identified in the year 2000. These objects are estimated to be between 600 and 700 kilometers wide. The discovery of these massive KBOs raised an important question. Was Pluto truly unique? Many scientists began to argue that Pluto was just one of many large bodies in the Kuiper belt. Not only were some of these newly found objects similar in size, but they also shared other characteristics with Pluto. Some had moons of their own, and their surface compositions were strikingly alike, featuring frozen methane and carbon monoxide. This situation mirrored the earlier case of Ceres, which was initially classified as a planet before astronomers realized it was just one of many objects in the asteroid belt. The debate intensified with the discovery of Eris, a distant object in an area called the scattered disk, even farther from the Sun than the Kuiper belt. Scientists soon realized that Eris was about 27% more massive than Pluto. Initially, Eris was also thought to be larger than Pluto, though the New Horizons spacecraft later confirmed that Pluto was slightly bigger in size. This discovery forced the International Astronomical Union, IAU, to redefine what it means to be a planet. According to their new definition, a planet must clear its neighborhood, meaning it must be the dominant object in its orbit. Since Pluto shares its orbital space with many other large KBOs, it did not meet this requirement and was officially reclassified as a dwarf planet, making it one of the most famous members of the Kuiper belt. To this day, it is uncertain how many Kuiper belt objects qualify as dwarf planets. While Pluto, Haumea, Makemake, Quaoar, and another large KBO named Orcus are widely accepted as dwarf planets, astronomers have suggested that others, including Salacia and 2 objects known as 2002 MS4 and 2002 AW197, might also meet the criteria. A fascinating pattern has emerged among these large KBOs. Many of them have moons. The 6 largest known trans-Neptunian objects, Eris, Pluto, Gong-Gong, Makemake, Haumea, and Quaoar, are all accompanied by at least one natural satellite, with 2 of them having multiple moons. This suggests that larger KBOs may have formed differently from their smaller counterparts. Another interesting feature of the Kuiper belt is the high number of binary systems, where 2 objects of similar size orbit around a shared center of mass. The most famous example is Pluto and its moon Charon, which are so close in mass that they almost function as a double planet, Scientists estimate that around 11% of all KBOs exist in these binary pairs. The first spacecraft sent to explore the Kuiper belt, New Horizons, was launched on the 19th of January in the year 2006. It made history by flying past Pluto on the 14th of July in the year 2015, capturing stunning images and revealing details about Pluto's surface, atmosphere, and moons. But its mission was far from over. After passing Pluto, New Horizons continued deeper into the Kuiper belt, searching for other distant objects to study. On the 15th of October in the year 2014, astronomers using the Hubble Space Telescope identified 3 potential targets for New Horizons. These objects, temporarily named PT-1, PT-2, and PT-3, were too small to be seen with ground-based telescopes. They ranged between 30 and 55 kilometers in diameter and were located at a distance of approximately 43 to 44 astronomical units from the Sun, 1 astronomical unit being the distance between Earth and the Sun. Among these candidates, PT-1, later given the designation 2014 MU69, was selected as the best target for New Horizons. In late October and early November of the year 2015, the spacecraft made a series of course adjustments to ensure a close flyby. This event took place in January of the year 2019, making PT-1, later named Arrokoth, the most distant object ever explored up close by a spacecraft. During its extended mission, New Horizons also detected another distant Kuiper belt object, originally named 1994 JR1 and later given the official name 15,810 Arawn. The spacecraft captured images of this object from an incredible distance of 270 million kilometers. On the first day of January in the year 2019, NASA's New Horizons spacecraft completed a historic flyby of Arrokoth, a mysterious object deep in the Kuiper belt. The data it sent back revealed that Arrokoth is shaped like 2 smaller bodies stuck together, forming what scientists call a contact binary. It measures about 32 kilometers in length and 16 kilometers in width. One of the instruments on board, named Ralph, confirmed that Arrokoth has a reddish color. However, analyzing all the information collected from this encounter would take nearly 20 months as the spacecraft continued sending data back to Earth. Despite the success of New Horizons, there are currently no plans to send another mission to explore Pluto in detail. However, scientists have considered at least 2 ideas for spacecraft that could either orbit or land on Pluto in the future. Beyond Pluto, many other fascinating objects exist in the Kuiper belt, including the dwarf planets Mugmug and Haumea. These celestial bodies are too far for New Horizons to visit, but future missions could be designed specifically to study them. One major aerospace company, Thales Alenia Space, has explored the possibility of sending an orbiter to Haumea. This distant world is of particular interest because it is the largest member of a group of space objects believed to have formed from the same ancient collision. Haumea is also unique because it has a ring around it and 2 small moons. A lead researcher, Joel Ponce, has suggested that developing new space technology could make it possible for spacecraft to reach and orbit Kuiper belt objects in as little as 10 to 20 years. Alan Stern, the principal investigator of New Horizons, has informally proposed an idea to send a spacecraft that would first fly past the ice giants Uranus or Neptune before heading toward new Kuiper belt objects. Such a mission would allow scientists to explore these enormous, distant planets for the first time since NASA's Voyager 2 spacecraft visited them back in the 1980s. One particularly interesting Kuiper belt object, Umuamua, has been considered as a potential flyby target for a future spacecraft designed to study the interstellar medium, the vast space beyond our solar system. At the Johns Hopkins Applied Physics Laboratory, scientist Pontus Brandt and his team have been developing ideas for a mission that could reach Quaoar in the decade of the 2030s. From there, the probe would continue its journey beyond our solar system, passing through a region known as the heliospheric nose. Scientists are especially interested in Quaoar because it appears to have a thin methane atmosphere that may be gradually disappearing. There is also evidence that it has experienced cryovolcanism, a process where icy volcanoes erupt instead of the lava seen on Earth. The proposed mission by Brandt and his team would launch using NASA's Space Launch System, SLS, and reach a speed of 30 kilometers per second by using Jupiter's powerful gravity to slingshot it forward. Another study published in the year 2012 examined the possibility of an orbiter mission to two other Kuiper belt objects, Ixion and Huya. The calculations showed that if launched in the year 2039, a spacecraft could reach Ixion after a journey of about 17 years. Astronomers have also been looking beyond our solar system to find similar structures around other stars. By the year 2006, scientists had discovered dust rings around 9 different stars, which they believe resemble our Kuiper belt. These distant belts appear to fall into 2 categories. Some are wide, stretching more than 50 times the distance between the Earth and the Sun, while others are much narrower, measuring between 20 and 30 times that distance. In addition, between 15 and 20% of stars similar to our Sun show signs of having large Kuiper belt-like structures. Most of these dusty rings are found around relatively young stars. However, 2 images taken by the Hubble Space Telescope in the first month of the year 2006 captured much older structures, around 300 million years old, showing that they have settled into stable shapes. One of the images provides a top-down view of a wide belt, while the other shows a side view of a narrower belt. Computer simulations suggest that our own Kuiper belt may have looked like these narrow rings when it was much younger. This ongoing research shows that the Kuiper belt is not just a mysterious region in our solar system, it may be part of a much bigger story about how planetary systems form and evolve throughout the universe. Planet 9 is an unseen yet intriguing planet that scientists believe might be lurking in the farthest reaches of our solar system. It is called a hypothetical planet because no one has actually spotted it yet, but its possible effects on other space objects have led researchers to suspect it exists. Deep beyond Neptune, there are mysterious icy bodies known as extreme trans-Neptunian objects. These distant space travelers follow strange, clustered orbits, moving in a way that suggests they might be under the influence of a hidden planetary force. Their paths tilt similarly, and they all seem to swing closest to the Sun in the same general region. This unusual pattern has led many scientists to propose that an undiscovered giant planet is quietly shaping the motion of these objects, much like a shepherd guiding its flock. However, not everyone is convinced. Some experts argue that this strange clustering might not be due to an invisible planet at all, but rather a trick of observation. Since these distant objects are extremely hard to detect and track throughout the year, it is possible that their unusual movements are simply an illusion created by the way astronomers observe them. If Planet 9 is real, it is estimated to be a supersized version of Earth, perhaps between 5 and 10 times as massive. Scientists believe it follows an incredibly elongated path around the Sun at a distance far beyond Neptune. Earlier predictions suggested its orbit might stretch anywhere between 400 and 800 times the distance between Earth and the Sun. More recent studies have refined that estimate, suggesting Planet 9 might be orbiting at an average distance of 460 times the Earth-Sun distance. However, in the year 2025, new calculations revised this distance to 290 times the Earth-Sun distance, with some margin for error. How did such a planet end up so far from the Sun? One theory suggests that during the early days of the solar system, this giant planet was flung outward by Jupiter's immense gravity. Another idea is that it was once a wandering rogue planet, floating through space, until our Sun captured it. Some even believe that a passing star might have pulled it into its current orbit long ago. Despite several large-scale searches of the sky using powerful telescopes such as the Wide Field Infrared Survey Explorer, WISE, and Pan-STARRS, No one has yet found direct evidence of Planet 9. However, these surveys have not ruled out the possibility that a Neptune-sized world might still be hiding in the cold, dark reaches of space. Scientists continue their search with newer tools, including the 8-meter-wide Subaru telescope and the NEOWISE survey. Until someone actually spots it, the existence of Planet 9 remains an open question, and alternative explanations for the strange orbital clustering of distant objects are still being explored. The idea of a hidden planet beyond Neptune is not new. In fact, ever since Neptune was discovered in the year 1846, astronomers have wondered if there might be yet another planet lurking beyond. The most famous of these ideas came from Percival Lowell, who spent years calculating where such a planet might be. In the year 1906, he began searching for what he called Planet X. Decades later, in the year 1930, astronomer Clyde Tombaugh continued this search and found Pluto. But Pluto turned out to be too small to explain the oddities in Uranus and Neptune's orbits, meaning Lowell's elusive Planet X remained undiscovered. In the late 20th century, new data from the Voyager 2 spacecraft helped solve part of this mystery. It turned out that scientists had been using the wrong mass for Neptune in their calculations. When they corrected it, the unexplained wobble in Uranus's orbit disappeared, making it seem like there was no need for a hidden planet after all. Still, the hunt for planets beyond Neptune did not stop. Even before Pluto was found, astronomers had been trying to detect unseen worlds by studying their effects on other objects. In the year 1880, George Forbes proposed that 2 hidden planets might exist. One, he said, could be orbiting the Sun at a distance of 100 times that of Earth, while the other might be even farther, at 300 times the Earth-Sun distance. Forbes's ideas were similar to today's Planet 9 theories, because he also believed these distant planets could be causing small objects to cluster together in space. The search for unseen worlds got a boost in the year 2004 with the discovery of Sedna, a strange dwarf planet with an incredibly distant orbit. Unlike other small worlds influenced by Neptune's gravity, Sedna's closest approach to the Sun is still an astonishing 76 times the Earth-Sun distance. That means something else, perhaps a massive, undiscovered planet, may have placed Sedna in this orbit long ago. Then, in the year 2014, astronomers found another distant object, named 2012 VP-113, which had an even farther perihelion. Its closest point to the Sun was 80 times the Earth-Sun distance. This fueled new speculation that a mysterious, giant planet was lurking in the outer reaches of the solar system, subtly pulling these objects into their unusual orbits. At a scientific conference in the year 2012, astronomer Rodney Gomez proposed that an invisible planet, as massive as Neptune, could be responsible for the odd paths of some trans-Neptunian objects. According to his calculations, this unseen world would be orbiting at about 1,500 times the Earth-Sun distance on a tilted and highly elongated path. If such a planet existed, it could explain why certain distant objects, including some centaurs, which are small celestial bodies crossing the paths of giant planets, behave in such peculiar ways. A year later, in the year 2015, Gomez and his colleagues published a detailed paper outlining their case for this unseen planet. Since then, more evidence has surfaced, but without direct observation, the mystery remains unsolved. Back in the year 2014, astronomers Chad Trujillo and Scott S. Shepard noticed something unusual. They saw that the orbits of 2 distant celestial bodies, Sedna and another object known as 2012 VP-113, along with several other extreme trans-Neptunian objects, ETNOs, shared a striking similarity. This pattern was so odd that they proposed a bold idea: an unknown planet, far beyond Neptune, might be pulling on these objects with its gravity. They suggested that this hidden world could be orbiting the Sun in a nearly circular path, somewhere between 200 and 300 times the distance from Earth to the Sun, astronomical units, or AU. Later that same year, two other astronomers, Raúl and Carlos de la Fuente Marcos, took things even further. They argued that one hidden planet wouldn't be enough to explain these mysterious orbits. Instead, they believed there had to be two massive planets locked in a gravitational dance, influencing a total of 13 known etnos at that time. By analyzing a larger sample of 39 such objects, they estimated that the closer of these planets had an orbit stretching between 300 and 400 AU, with only a slight oval shape and a tilt of about 14 degrees. Then, in early 2016, scientists Konstantin Batygin and Mike Brown from the California Institute of Technology proposed an even more refined theory. They showed that the peculiar clustering of 6 etnos could be explained by a single hidden planet, one they called Planet 9. They even suggested what its orbit might look like. According to their calculations, Planet 9's gravity could also explain why some distant objects have orbits perpendicular to the rest of the solar system and why some have extreme tilts. Even more intriguing, this mysterious world could be the reason why the Sun itself appears slightly tilted relative to the planets that orbit it. At first, scientists believed that Planet 9 traveled around the Sun in a stretched-out elliptical orbit, with an eccentricity between 0.2 and 0.5. This means that instead of moving in a perfect circle, its path would be slightly elongated. The planet's estimated distance from the Sun ranged from 400 to 800 AU, meaning it would be 13 to 26 times farther than Neptune. If it truly exists, this mysterious world would take an astonishing 10,000 to 20,000 years to complete a single orbit around the Sun. Scientists also predicted that its orbit was tilted between 15 and 25 degrees compared to Earth's orbital plane. If Planet 9 is real, then its farthest point from the Sun, its aphelion, would be in the general direction of the Taurus constellation. Meanwhile, its closest point to the Sun, its perihelion, would be somewhere near the southern regions of the constellations Serpens Caput, Ophiuchus, and Lyra. Mike Brown, one of the leading researchers on Planet 9, believes that if we could confirm its existence, a spacecraft using a special slingshot maneuver around the Sun could reach it in as little as 20 years. As for the planet's size, estimates suggest that it is about 5 to 10 times heavier than Earth and has a diameter about 2 to 4 times that of our home planet. Brown also thinks that if it does exist, it has been around long enough, about 4.5 billion years, the same age as the solar system, to clear its orbit of other large objects. Because of this, its gravity dominates the outer solar system, which would qualify it as a planet by modern scientific definitions. Astronomer Jean-Luc Margot also agrees, stating that if we ever detect Planet 9, it would unquestionably be classified as a planet. As research continued, scientists kept refining their predictions. By the year 2025, Amir Siraj and his colleagues proposed a slightly different estimate for Planet 9's mass, suggesting it could be around 4.4 times the mass of Earth, with a possible variation of plus or minus 1.1 Earth masses. Another team of researchers, Esther Linder and Christophe Mordacini, took a different approach. Based on their calculations and observations from distant exoplanets, they predicted that Planet 9's radius would be about 3.66 times that of Earth, which means roughly 23,300 kilometers across. If they were right, then Planet 9's composition would be similar to that of Neptune and Uranus, with a thick atmosphere made mostly of hydrogen and helium. The temperature on this distant world would be freezing, around 47 Kelvin, which is extremely cold by human standards. Beneath this atmosphere, they believed, the planet would have a rocky core of iron and a mantle rich in magnesium silicate and water ice. However, Siraj and his team offered a different perspective. They suggested that Planet 9 might actually be more like Earth, a rocky world instead of a gas giant. If true, this would change our understanding of what kind of planets can exist in the far reaches of the solar system. But where did Planet 9 come from? Scientists have debated several possible origins. Some believe it may have started out much closer to the Sun, forming near the giant planets like Jupiter and Saturn. At some point, they propose, a close encounter with one of these gas giants flung it out to the distant regions of space. Over time, gravitational influences from passing stars or even remnants of the early solar system could have stabilized its orbit, preventing it from escaping completely. Others think Planet 9 could have come from beyond our solar system, possibly captured from another star. Alternatively, it might have formed right where it is today, but that would require an unusually massive and extended disk of material in the early solar system. Some researchers suggest that a dense disk of icy planetesimals could have helped slow Planet 9 down, allowing it to settle into its current orbit. Another possibility is that a passing star could have altered its orbit, shifting it from a circular path to a more elongated one. If Planet 9 did form so far away, it would have had to gather material from a narrow ring of dust and ice, slowly growing over 1 billion years. However, there's only about a 10% chance that a planet forming at such a great distance would have remained bound to the Sun after the Sun left its original birth cluster. Scientists believe that Planet 9 might not have originally belonged to our solar system. Instead, it could have been pulled in from another star system during a rare cosmic event, a close encounter between the Sun and a passing star. If that star had a planet in a distant orbit, the gravitational forces from both stars could have altered its trajectory, capturing it into orbit around the Sun. This would have been more likely if the other star system lacked a giant planet like Jupiter, which usually disrupts such events. However, even under ideal conditions, the chances of capturing a planet into an orbit like Planet 9's are only about 1 to 2%. Astrophysicists Amir Siraj and Avi Loeb suggested that if the Sun once had a twin, a distant star of equal mass orbiting alongside it, then the chances of capturing Planet 9 would have increased by a factor of 20. This kind of capture could also happen with rogue planets, planets that drift through space without a star, but the likelihood of that happening is far lower, estimated at only 0.05 to 0.1%. Planet 9 was first proposed as an explanation for a strange phenomenon. The orbits of certain icy objects in the outer solar system seem to be clustering together in an unusual pattern. This clustering also seemed to explain why objects like Sedna have such high perihelia, the closest point to the Sun in their orbits. Scientists were initially puzzled when they discovered that some of these distant objects moved in nearly perpendicular orbits, but upon further analysis, their movements matched observations of real objects. When astronomers ran computer simulations that included all the known planets, they found that some of these objects' orbits gradually shrank over time. Although other explanations have been suggested for these unusual orbital patterns, the gravitational pull of an undiscovered planet remains the most compelling explanation. If Planet 9 exists, its gravity would also influence other objects crossing its path, scattering them into different orbits. This could explain why some scattered disk objects, icy bodies beyond Neptune with orbits stretching more than 50 times the Earth-Sun distance, appear in broader and more varied orbits than expected. At one point, scientists even speculated that Planet 9 might be responsible for tilting the Sun's axis by 6 degrees relative to the planet's orbits. However, more recent calculations suggest its effect on the Sun's tilt would be much smaller, at around 1 degree. The first clues about Planet 9's possible existence came from astronomers Scott Shepard and Chad Trujillo, who noticed that two distant objects, Sedna and a body named 2012 VP113, had strikingly similar orbits. In theory, without a hidden planet's influence, the orbits of such distant objects should be randomly distributed across the sky. But when Shepard and Trujillo analyzed a dozen trans-Neptunian objects, TNOs, With perihelia beyond 30 times the Earth-Sun distance and semi-major axes beyond 150 times that distance, they found a surprising pattern. All of them had their closest points to the Sun aligned in the same general direction, clustering around 0 degrees. Shepard and Trujillo suggested that a massive, undiscovered planet beyond Neptune was influencing these objects, possibly through a gravitational effect called the Kozai mechanism. This mechanism forces objects with similar semi-major axes to have their closest approaches to the Sun aligned at either 0 degrees or 180 degrees. This would prevent them from getting too close to the hidden planet, as they would only cross its orbit when they were either far above or far below it. However, later studies refined their hypothesis with new evidence. Another pair of scientists, Konstantin Batygin and Michael Brown, set out to challenge Shepard and Trujillo's theory. They carefully examined the orbits of distant TNOs, eliminating any that might have been influenced by Neptune's gravity. After filtering out these cases, they found that the remaining 6 objects, including Sedna and 2012 VP113, had perihelia clustered around 318 degrees, plus or minus 8 degrees. This did not match the predictions of the Kozai mechanism, which would have placed them near 0 or 180 degrees. Batygin and Brown also noticed another strange alignment. When they looked at the 6 most distant extreme trans-Neptunian objects, ETNOs, with semi-major axes beyond 250 times the Earth-Sun distance, their orbits all pointed in the same general direction. Even more remarkably, their orbits were all tilted in a similar way relative to the rest of the solar system. The odds of this happening by pure chance were incredibly low, only about 0.007%. The discovery was even more intriguing because these 6 objects had been found by different telescopes in separate studies, meaning the pattern was unlikely to be caused by biased observations. Normally, over hundreds of millions of years, the orbits of such objects should shift due to natural gravitational effects. If the clustering was caused by a past event, like a passing star, it should have dispersed by now. Since the pattern is still present, scientists believe it is likely being maintained by the gravitational pull of a massive yet unseen planet orbiting the Sun. 2 of the objects, 2013 RF98 and Alicanto, had nearly identical orbits and spectra, which led astronomers to propose that they might have once been a binary pair. If so, they could have been torn apart when they passed near another distant object. However, such an event would require an extremely close encounter, making it a rare occurrence at such great distances from the Sun. In a later study, Shepard and Trujillo discovered another intriguing correlation among TNOs with semi-major axes greater than 150 times the Earth-Sun distance. They found that objects with longitudes of perihelion between 0 and 120 degrees tended to have arguments of perihelion between 280 and 360 degrees. Meanwhile, those with longitudes of perihelion between 180 and 340 degrees had arguments of perihelion between 0 and 40 degrees. The probability of this pattern occurring by chance was an astonishing 99.99%. Shepard and Trujillo suggested that this correlation might be due to the orbits of these objects adjusting to avoid close encounters with a massive planet. This would further support the idea that an undiscovered world, Planet 9, could be lurking in the far reaches of our solar system, waiting to be found. In the year 2017, scientists Carlos and Raúl de la Fuente Marcos published an article discussing the unusual patterns observed in the orbits of extreme trans-Neptunian objects, or ETNOs for short. These are icy bodies that orbit the Sun far beyond Neptune. The researchers noticed something interesting. When they studied the distances at which these objects cross the plane of the solar system, their distribution appeared to follow a pattern with 2 peaks instead of just 1. This also seemed to be true for centaurs, icy bodies that travel between the orbits of giant planets, and for comets with very elongated orbits. The scientists proposed that this strange pattern might be the result of ETNOs instinctively avoiding getting too close to a large, unseen planet that orbits the Sun, somewhere between 300 and 400 astronomical units away. As astronomers gathered more data, increasing the sample size to 40 objects, they found an unexpected asymmetry in how the ETNOs' orbits aligned. Specifically, there was a noticeable difference in the distances between where these objects' orbits crossed the plane of the solar system in an upward direction versus where they crossed downward. This difference was statistically significant, meaning it was unlikely to be just a coincidence or an error caused by limited observations. Instead, it suggested that something, perhaps the gravitational pull of a hidden planet, was influencing these distant objects. Scientists had already been running computer simulations to see if a massive unseen planet, known as Planet 9, could explain these orbital patterns. The simulations, conducted by astronomers Konstantin Batygin and Mike Brown, showed that if a giant planet with a highly stretched-out orbit were lurking far beyond Neptune, it could sculpt the orbits of these scattered icy objects. Over time, the gravitational influence of this hypothetical planet would cause the orbits of many ETNOs to cluster together in a similar direction, rather than being randomly spread out. The simulations also showed that some of these objects would be pushed into orbits similar to that of Sedna, an enigmatic celestial body that never gets close to Neptune, while others ended up in orbits at right angles to the rest, a phenomenon that astronomers later confirmed in real observations. Batygin and Brown initially focused on 6 particularly distant ETNOs and found that their orbits best matched a simulation where Planet 9 had a mass around 10 times that of Earth. The gravitational effects of such a planet would vary, depending on how far out an object orbits. For instance, objects with orbits extending beyond 250 astronomical units were strongly anti-aligned with Planet 9, meaning their closest approach to the Sun happened in the opposite direction from where Planet 9's closest approach would be. Meanwhile, objects with orbits between 150 and 250 astronomical units showed a weaker alignment, with their closest approach to the Sun happening in the same direction as Planet 9's. However, objects orbiting closer than 150 astronomical units seemed to be unaffected. The scientists tested various possibilities for Planet 9's orbit, trying different distances between 400 and 1,500 astronomical units, different levels of oval-shaped elongation or eccentricity, and various tilts. They found that if Planet 9 had a steeply tilted orbit, it could explain why ETNOs tended to have similar tilts themselves. However, this also reduced the anti-alignment effect. Another study by researcher Catherine Volk-Becker and her colleagues suggested that if Planet 9 had a less stretched-out orbit, the ETNOs' orbits were more stable. But if the hidden planet had a more eccentric orbit, then anti-alignment was more pronounced. Other studies revealed additional details. A study by Michelle Lawler and her team suggested that if Planet 9 had a perfectly circular orbit, it would capture fewer ETNOs into stable gravitational patterns, and fewer objects would end up in highly tilted orbits. Meanwhile, research by Hector Carteres and colleagues showed that if Planet 9's closest approach to the Sun was lower, it could better explain the alignment of ETNO orbits, but only if its closest distance was still more than 90 astronomical units. Later, Batygin and his colleagues found that if Planet 9 had a highly stretched-out orbit, the average tilt of ETNO's orbits would be reduced. Despite these variations, none of the alternative simulations could explain the observed orbital alignments as well as the original Planet 9 model. To improve predictions about where this hidden planet might be, astronomers need to find and study more distant celestial objects. If additional data matches what the simulations predict, it would further support the idea that Planet 9 exists. But if new observations contradict these predictions, it might suggest that another explanation is needed. When astronomers included the effect of giant planets like Jupiter and Saturn moving over time, they found that the alignment of ETNO's orbits became weaker. Additionally, the direction of the alignment switched, meaning that objects with larger orbits tended to be more anti-aligned with Planet 9, while those with higher perihelia, meaning their closest approach to the Sun was farther out, were instead more aligned. This could mean that the so-called sednoids, like Sedna and other similar objects, might have orbits opposite to most other etnos. Planet 9, if it exists, would influence etnos in multiple ways. Over hundreds of millions of years, it would exert a slow but powerful force on their orbits, causing their closest approaches to the Sun to gradually move outward, placing them in Sedna-like orbits. Then, over another long period, they would slowly return to their original orbits. On a shorter timescale, these objects would also interact with Planet 9 through a process called mean motion resonance, which helps keep their orbits stable. This mechanism slightly adjusts their orbital distances, ensuring they don't get too close to Planet 9 and are instead kept in a synchronized rhythm with it. However, this protective effect isn't perfect. The gravitational pull of Neptune and the other giant planets, combined with the fact that Planet 9's orbit is likely tilted, weakens this stabilizing mechanism. This leads to chaotic changes in the object's orbits over millions of years as they shift between different gravitational interactions. Some of these changes happen in unusual orbital patterns, such as the 27-17 resonance, meaning that for every 27 times one object orbits the Sun, another does it 17 times. Interestingly, the orbits of etnos also appear to precess, meaning their orbital poles gradually circle around a larger gravitational reference point called the solar system's Laplace plane. When objects orbit far enough from the Sun, this Laplace plane is slightly tilted toward Planet 9's orbital plane, which helps explain why etnos tend to have their orbits clustered in a certain direction. In the year 2024, scientists Mike Brown and Konstantin Batygin ran a computer simulation that suggested the mysterious Planet 9 could have a powerful effect on certain distant objects in our solar system. Their research showed that over long periods, this hidden planet's gravity could stretch and distort the orbits of space objects that orbit far beyond Neptune. Specifically, they found that objects with major orbital paths extending beyond 100 times the Earth-Sun distance, 100 astronomical units, would, over time, be pulled into paths that cross Neptune's orbit. This would happen as their closest approach to the Sun, known as their perihelion, dropped below 30 astronomical units. To test their theory, Brown and Batygin also conducted a detailed survey of objects that already cross Neptune's path, but have tilted orbits below 40 degrees and semi-major axes between 100 and 1,000 astronomical units. Their findings suggested that if Planet 9 exists, it would create a specific pattern. About 3% of Neptune-crossing objects should exist, compared to only 0.5% if Planet 9 were not there. One of the more fascinating effects of Planet 9 is how it appears to force certain space objects into bizarre, highly tilted orbits. Some of these objects, called extreme trans-Neptunian objects, ETNOs, end up with their orbits tilted at angles of over 50 degrees, and in some cases even perpendicular to the normal plane of the solar system. Scientists have observed multiple objects with massive orbits stretching beyond 250 astronomical units that fit this pattern. Their study found that when certain etnos start with low-tilt, circular orbits, they can become trapped by Planet 9's gravitational influence. This sets off a chain reaction where their orbits become stretched and more tilted, pushing them into nearly vertical orbits. Eventually, some of these objects shift into retrograde orbits, meaning they move in the opposite direction of the planets before looping back into their original states. Simulations suggested that this kind of orbital dance happens fairly often, with about 38% of affected objects experiencing at least one cycle. The study also suggests that a separate group of highly tilted trans-Neptunian objects, TNOs, with orbital paths extending less than 100 astronomical units, may have been influenced by both Planet 9 and the larger planets like Neptune and Jupiter. These etnos, after being pulled into nearly vertical orbits, can have their paths altered by close encounters with Neptune or other giant planets. If this happens, their orbits shrink below 100 astronomical units, making them no longer controlled by Planet 9. An example of this process is an object known as 2008 KV-42. Researchers believe that some of these objects may have originally come from the Oort cloud, a distant shell of icy bodies surrounding the solar system, but their simulations showed that the Oort cloud alone could not explain the number of objects seen today. Planet 9's gravitational influence would also shape the way comets travel through the solar system. Simulations based on the NICE model, which describes how giant planets like Jupiter and Saturn moved in the past, suggest that Planet 9 would reduce the number of objects captured in the Oort cloud. Instead, it would create its own cloud of objects, stretching from 200 to 3,000 astronomical units, consisting of ETNOs and perpendicular objects. Some of these objects, when their orbits shift closer to the Sun, could become the comets we observe. If Planet 9 exists, it may be responsible for as much as 1/3 of the Halley-type comets that enter the inner solar system. Additionally, Planet 9's presence would likely increase the number of scattered disk objects with moderate inclinations between 15 and 30 degrees. However, recent estimates suggesting Planet 9 has a smaller mass and less eccentric orbit might mean its influence on these objects is weaker than previously thought. Despite the compelling evidence, some scientists remain skeptical. Batygin himself cautioned that until astronomers capture direct images of Planet 9, its existence is still just a strong hypothesis. He described the current state of research as an echo of something that might be there. Back in 2016, Brown estimated that the odds of Planet 9 being real were around 90%, while astronomer Greg Laughlin, who reviewed the research before publication, placed the probability at 68.3%. However, other scientists demand more observational data before making any conclusions, insisting that more Kuiper belt objects, KBOs, need to be analyzed or that a telescope must finally capture Planet 9 in an image. Brown, while acknowledging these concerns, still believes there is enough evidence to justify an extensive search for this hidden world. The theory of Planet 9 has gained significant support among the scientific community. In January 2016, Jim Green, who was then the director of NASA's Science Mission Directorate, stated that the evidence is stronger now than it's been before. However, he also warned that alternative explanations for the observed orbital patterns of distant objects should not be ruled out. Echoing Carl Sagan's famous words, he emphasized that extraordinary claims require extraordinary evidence. Meanwhile, Massachusetts Institute of Technology professor Tom Levinson suggested that, at this moment, Planet 9 appears to be the best explanation for the strange behavior of the solar system's outermost objects. Astronomer Alessandro Morbidelli, who reviewed the research before publication in the Astronomical Journal, also agreed, saying, "I don't see any alternative explanation to that offered by Batygin and Brown." Astronomer Renu Malhotra remains open-minded about the existence of Planet 9. She hasn't taken a firm stance for or against it, but she and her team have observed something unusual in the way certain distant objects, called extreme trans-Neptunian objects, ETNOs, move. Their orbits appear to be tilted in a way that doesn't make sense based on what scientists currently know. Malhotra described it as astonishing, saying, "The amount of distortion we see is just unbelievable." In her view, this is the most convincing clue she has encountered so far that suggests Planet 9 might be real. Not all scientists agree, though. Some are skeptical, meaning they doubt whether Planet 9 actually exists. One of them is American astrophysicist Ethan Siegel. In the past, Siegel proposed that some planets might have been thrown out of the solar system due to chaotic events in its early history. However, he doesn't believe an unknown planet is still lurking out there. In an article written in the year 2018, Siegel discussed a scientific survey that found no clear pattern in the orbits of ETNOs. He suggested that earlier claims of clustering might have been due to observational bias, essentially errors in the way data was collected rather than real evidence of a hidden planet. He also pointed out that most scientists do not support the idea that Planet 9 exists. Another planetary scientist, Hal Leveson, weighed in on the debate. He estimated that if an object had been kicked out of its original position in the solar system, there was only about a 2% chance that it would end up in the inner part of the Oort cloud, a distant region filled with icy bodies. He also speculated that if such an object really did exist, many others must have been ejected even farther away, possibly beyond the Oort cloud itself. By the year 2020, skepticism surrounding the Planet 9 theory grew even stronger. Two major scientific surveys, the Outer Solar System Origins Survey, OSOS, and the Dark Energy Survey, DES, examined the orbits of hundreds of trans-Neptunian objects. OSOS alone documented over 800 such objects, while DES discovered 316 new ones. After carefully correcting for observational biases, both studies concluded there was no real evidence that these objects' orbits were clustering due to the presence of a hidden planet. Instead, they found that the orbits could be explained by known physical forces, such as interactions with other planets. One of the researchers involved, Samantha Lawler, challenged the original theory proposed by scientists Mike Brown and Konstantin Batygin. She argued that their conclusions were based on a much smaller dataset, only 14 objects, while the newer studies had a far larger sample size of 800. Lawler stated that trying to confirm Planet 9's existence based on such limited data was premature. She also proposed another explanation. The odd orbital patterns of these objects might be linked to Neptune's gravitational pull from when it slowly moved outward in the distant past. However, despite these doubts, some researchers still believe in the possibility of Planet 9. One theory suggests that it could be a leftover from the solar system's early days. According to a model called the 5-planet NICE model, our solar system may have once contained 5 giant planets: Jupiter, Saturn, Uranus, Neptune, and a mysterious 5th planet that is no longer there. Computer simulations of this model suggest that about 4 billion years ago, gravitational forces caused this 5th planet to be ejected from the inner solar system. Some scientists believe that instead of being completely thrown out, this missing planet could still be orbiting far beyond Neptune. This is what they think Planet 9 might be. The idea that Planet 9 could be the long-lost 5th giant is supported by its estimated size and orbit, which match what scientists would expect from an ice giant. Computer models of the NICE model also show that when a planet gets ejected, it can leave behind a gravitational footprint, altering the orbits of other planets and smaller objects. Some believe that the strange clustering of trans-Neptunian objects could be an indirect sign of Planet 9's gravitational influence. If this planet was still present in the outer reaches of the solar system, it could explain why some objects seem to move in a coordinated way. Even so, the Outer Solar System Survey, OSSOS, found no strong evidence to support this idea. After analyzing 8 objects that had very distant orbits, each with a semi-major axis longer than 150 times the distance from the Earth to the Sun, they concluded that their movements were randomly distributed, rather than showing signs of a hidden planet's pull. Pedro Bernardinelli and his team, working with data from the Dark Energy Survey, also failed to find any clear clustering in the orbits of ETNOs. However, they admitted that their study didn't completely rule out Planet 9, since the number of objects they examined wasn't large enough to reach a final conclusion. Interestingly, earlier studies led by Mike Brown suggested that when all observational biases were considered, the unusual clustering of certain objects was highly unlikely to be a coincidence. He calculated that if these objects had randomly distributed orbits, the clustering observed should have only happened about 1.2% of the time. When combining this with other orbital characteristics, the probability dropped even further, to just 0.025%. A later study analyzing 14 objects revised this probability to 0.2%, still suggesting that something unusual is happening in the outer solar system. Scientists have been running complex computer simulations to test the idea of a hidden ninth planet lurking in the outer reaches of our solar system. By studying how 15 known distant objects move under the influence of this mysterious Planet 9, they noticed some unusual results that didn't quite match real-world observations. These findings have fueled an ongoing debate, with researchers divided over whether the unexplained patterns in these distant objects' movements point to an unseen planet or if another, more subtle force is at play. Astronomer Corey Shankman and his team created a simulation where they placed many hypothetical versions of these 15 distant objects into a digital model of the solar system. Each of these objects had orbits similar to the real ones seen in space, with their paths stretching more than 150 times the Earth-Sun distance and coming no closer than 30 times that distance. The researchers found that while some objects aligned in the opposite direction of Planet 9, as expected, other predicted patterns, such as a clustering effect in their closest approach points, did not appear. This inconsistency raised questions about whether the supposed gravitational influence of Planet 9 was really responsible for shaping these objects' orbits. Their simulation also revealed that some objects' orbits shifted in a way that would place them at distances between 50 and 70 times the Earth-Sun distance. However, in reality, no such objects have been observed in these locations, suggesting that if Planet 9 existed, it should have left behind more evidence than we currently see. The simulation also predicted a large number of objects with highly tilted orbits, which would have been missed by most telescopes since astronomers typically search along the flat plane of the solar system. Additionally, many objects in the model ended up being flung entirely out of the solar system after coming too close to the giant planets. Based on this, Shankman and his team estimated that the original collection of these far-out objects may have had a total mass equal to several times that of Earth, meaning that a much larger amount of material was likely ejected in the early history of the solar system. Ultimately, they concluded that Planet 9 might not exist and that the clustering of distant objects' orbits might just be a temporary coincidence that will disappear as more are discovered. However, not all scientists agree. Anne-Marie Madigan and Michael McCourt have proposed a different explanation that doesn't require Planet 9. They suggest that a vast, distant disk of icy objects, something they call a Zderick-Madigan or ZM belt, could be responsible for the unusual orbital patterns seen in these distant objects. According to their theory, this belt, made up of objects with stretched-out orbits, could naturally organize itself over time due to its own gravitational pull. This process, called inclination instability, would gradually lift some objects above or below the usual plane of the solar system and align their closest approach points into a cone-like shape. They estimate that for this to happen, the belt would have to contain at least 20 times the mass of Earth and have been in place for about 1 billion years. Some astronomers believe that already discovered objects like Sedna and 2012 VP-113 might be members of this mysterious belt. If true, thousands more objects like them could be waiting to be found. However, other scientists remain skeptical. Mike Brown, one of the main supporters of the Planet 9 theory, argues that current telescopic surveys have not found enough distant objects to support this inclination instability idea. He points out that in computer models of the solar system that include the gravitational effects of such a disk, this kind of instability does not appear. Instead, those simulations show that the object's orbits shift too quickly, and many of them are ejected before any meaningful clustering can occur. Additionally, he notes that the ZM belt theory requires an extremely specific set of conditions that may not be realistic given what we know about the evolution of the solar system. Another pair of researchers, Intranik Safilian and Jihad Tuma, have a slightly different take on the matter. They suggest that instead of a scattered belt of objects, a massive disk of trans-Neptunian objects, containing about 10 times the mass of Earth, could be keeping the distant objects' orbits in place. This disk, they propose, would counteract the gravitational forces of the giant planets, keeping the orbits of the farthest known objects steady. However, skeptics like Mike Brown question whether such a disk could have remained stable for billions of years, while another researcher, Konstantin Batygin, doubts that there was ever enough material in the Kuiper belt to form such a structure in the first place. Batygin also questions why such a disk would have formed so far from the Sun and not closer, where more material would have been available during the solar system's early formation. Adding to the debate, Renu Malhotra, Catherine Volk, and Xianyu Wang propose yet another explanation. They suggest that 4 of the most distant detached objects, those with paths that take them more than 250 times the Earth-Sun distance, might be trapped in a gravitational dance with a hidden planet. Their calculations suggest that this planet, if it exists, would move in a relatively circular orbit at an angle of about 11 degrees to the rest of the solar system. Alternatively, if some of these distant objects' orbits are stabilized by a different gravitational effect, the hidden planet could be on a much steeper orbit, tilted at around 48 degrees. Meanwhile, astronomers Scott Shepard and Chad Trujillo suggested in the year 2014 that a large planet, moving in a nearly circular path somewhere between 200 and 300 times the Earth-Sun distance, might be responsible for the strange clustering of distant objects. Their idea came from noticing that 12 of these far-off objects all had a similar alignment in their closest approach points. Since their simulations showed that these alignments should naturally spread out over billions of years, they argued that a hidden planet must be keeping them in place. This hypothetical planet, they theorized, would use a gravitational effect called the Kozai mechanism to guide these distant objects' paths. However, their model required additional factors, such as a passing star in the distant past, to explain why there are no known objects with reversed alignments. Scientists have long wondered why some small icy bodies in the farthest reaches of our solar system, known as trans-Neptunian objects, TNOs, move in strangely similar orbits. Computer simulations have provided a clue. A single massive planet, far beyond Neptune, might be pulling these objects into their unusual paths. These early simulations were just a proof of concept, meaning they showed the basic idea but didn't pinpoint exactly where this planet might be or what its orbit looks like. In fact, there could be many different ways such a planet's orbit could be arranged. While these models didn't fully explain the precise way the smaller objects were clustering, they were groundbreaking because they were the first to suggest that an undiscovered giant planet might be shaping these distant orbits. This situation is reminiscent of what happened in the early 19th century when astronomer Alexis Bouvard noticed that Uranus wasn't moving quite as expected. He suspected the presence of another unknown planet affecting Uranus with its gravity, a prediction that ultimately led to the discovery of Neptune. A pair of astronomers, Raúl and Carlos de la Fuente Marcos, took this idea a step further. Instead of just one hidden planet, they proposed that 2 unknown planets might be working together in a synchronized way, or in resonance. They teamed up with another scientist, Sverre J. Arseth, to analyze the way the TNO's orbits lined up. Their study ruled out the possibility that this alignment was just a coincidence caused by the way astronomers observe these objects. Instead, they suggested that something massive, perhaps a planet with a size somewhere between Mars and Saturn, was lurking about 200 times farther from the Sun than Earth is. Like earlier researchers, they thought that a process called the Kozai mechanism might be keeping the TNOs in line. This same gravitational effect explains how Jupiter influences the orbit of a comet known as Comet 96 P. Machtholz. But their model struggled to explain why all the orbits matched up so neatly if only one unknown planet was involved. That led them to propose that this planet might itself be interacting with an even larger, more distant world, about 250 times farther from the Sun than Earth. Other scientists, including Konstantin Batygin and Michael Brown, pointed out a challenge with this idea. The Kozai mechanism would only work in a very specific mathematical way, where the planet's orbits fit an exact pattern. If multiple planets were involved, their orbits would need to be precisely tuned, making the explanation much more complicated. Then, in the year 2019, two physicists, Jakob Schultz and James Unwin, suggested a completely different possibility. What if the mysterious force shaping the TNO's orbits wasn't a planet at all, but a tiny black hole? Their study of gravitational lensing data, which looks at how light bends around invisible objects, revealed a surprising number of small, planet-sized objects floating near the center of our galaxy. They speculated that instead of being wandering planets, these could actually be primordial black holes, tiny black holes that may have formed shortly after the Big Bang. If this idea is correct, then rather than a planet orbiting far beyond Neptune, our solar system might contain one of these ancient black holes trapped by the sun's gravity. One reason this black hole might be so hard to find is that it would be extremely cold and wouldn't emit much light. However, Schultz and Unwin suggested that if it interacts with invisible dark matter, it might produce gamma rays, which could be detected by a space telescope called the Fermi Large Area Telescope. Not everyone is convinced. Konstantin Batygin responded to their theory by saying that while it's possible, there just isn't enough evidence yet to say that a black hole is more likely than a planet. Meanwhile, theoretical physicist Edward Witten proposed launching a fleet of tiny probes powered by radiation pressure to search for a black hole in our outer solar system. But other researchers, including Thiem Hoang and Avi Loeb, pointed out that signals from these probes would likely be drowned out by interference from interstellar dust and gas. Despite this, Loeb and another scientist, Amir Siraj, proposed a new way to look for these tiny black holes using the Vera C. Rubin Observatory, which could detect bursts of light from small black holes swallowing matter in deep space. In the year 2023, yet another explanation emerged. A modified version of Newton's gravity, called Modified Newtonian Dynamics, MOND, was suggested as a possible alternative to both the planet and the black hole ideas. This theory, which was originally developed to explain why galaxies rotate the way they do without needing dark matter, predicts that the orbits of distant objects like Kuiper belt objects, KBOs, would naturally cluster in a way that matches what astronomers have observed. So, if Planet 9 does exist, why hasn't anyone seen it? The answer lies in its vast distance from the Sun. Being so far away, it would reflect very little sunlight, making it nearly invisible to telescopes. Scientists estimate that its brightness, or apparent magnitude, would be fainter than 22, meaning it would be at least 600 times dimmer than Pluto. If the planet happens to be at the closest point in its orbit, called perihelion, astronomers might already have captured it in past telescope images without realizing it. But if it's at its farthest point, or aphelion, more than 600 times the distance between the Earth and the Sun, only the most powerful telescopes on Earth would have any chance of detecting it. Because planets move more slowly when they are farthest from the Sun, thanks to Kepler's second law of planetary motion, statistically speaking, Planet 9 is more likely to be near its aphelion. However, a study in the year 2019 suggested that if it exists, it might be smaller and closer than originally thought, making it a bit easier to find. Based on its estimated brightness, it could have an apparent magnitude between 21 and 22. With ongoing observations of the orbits of Kuiper belt objects, scientists are gradually narrowing down where Planet 9 might be hiding. According to Fred Adams, a professor at the University of Michigan, if astronomers keep collecting data at their current pace, they could either confirm the existence of Planet 9 or rule it out completely by the year 2035. For years, astronomers have been scanning the night sky in search of the elusive Planet 9, a mysterious and distant world that may be hiding at the edge of our solar system. The renowned planetary scientists Konstantin Batygin and Michael Brown have already combed through vast astronomical databases, eliminating many potential locations along the predicted path of this hidden planet. However, some key areas remain unsearched. These include the planet's farthest point from the Sun, where it would be so dim that current telescopes may struggle to detect it, and the densely packed plain of the Milky Way, where distinguishing it from countless background stars is extremely difficult. Their search has relied on powerful observatories and historical sky surveys. They examined data from the Catalina Sky Survey, which captured celestial objects as faint as magnitude 21 to 22, as well as the Pan-STARRS survey, which reached magnitude 21.5. They also reviewed infrared observations from NASA's Wide Field Infrared Survey Explorer, or WISE. Despite these efforts, no trace of Planet 9 has been found. In the year 2021, Batygin and Brown expanded their search by analyzing the first 3 years of data from the Zwicky Transient Facility, but the planet remained elusive. This extensive effort ruled out 56% of the possible locations where Planet 9 could be hiding, forcing scientists to refine their predictions and push the planet's estimated orbit even farther from the Sun. Other astronomers have taken up the challenge as well. David Gerdes, an expert in astronomical imaging and one of the developers behind the Dark Energy Survey camera, believes that software used to track distant solar system objects, such as the dwarf planet designated as 2014 UZ224, could potentially identify Planet 9 if it appeared in the survey's images. This ambitious project scanned a massive section of the southern sky, covering 1/4 of it in total. Meanwhile, graduate students Michael Medford and Danny Goldstein from the University of California, Berkeley, have been using an innovative technique that stacks multiple images taken at different times. By adjusting these images to match the predicted motion of Planet 9, they hope to enhance its visibility and reveal a faint moving object that would otherwise be lost in the background noise. Additional searches have been conducted using data from the WISE and NEO-WISE missions. But once again, Planet 9 was not detected. This investigation focused on areas of the sky away from the crowded galactic plane and targeted a specific infrared wavelength of 3.4 micrometers. Scientists estimate that if a planet with 10 times the mass of Earth were lurking in these regions, it should have been visible out to distances between 800 and 900 astronomical units from the Sun. In a separate effort, astronomers Melina Rice and Gregory Laughlin employed an advanced algorithm called shift stacking to analyze data collected by NASA's Transiting Exoplanet Survey Satellite, or TESS. Their study focused on 2 specific sectors of the sky, searching for not only Planet 9, but also other distant objects in the outer solar system. Although they did not find compelling evidence for the planet, their work led to the discovery of 17 new potential trans-Neptunian objects located at distances between 80 and 200 astronomical units. Follow-up observations with powerful ground-based telescopes are now needed to confirm whether these objects truly exist. However, early attempts to verify 2 of these candidates using the William Herschel telescope have failed. By the year 2022, another attempt to locate Planet 9 compared data from the infrared astronomical satellite IRAS and the Japanese Akari space telescope. Yet once again, the planet remained undetected. Astronomers noted that infrared observations in many parts of the sky are heavily contaminated by heat emissions from interstellar gas clouds, making it extremely difficult to identify the weak thermal glow of a distant planet, especially near the central bulge of the Milky Way. Since Planet 9 is predicted to be most visible from the northern hemisphere, the most promising search efforts are expected to come from the Subaru telescope in Hawaii. This observatory is ideal for the task because it has both a large aperture capable of capturing faint light and a wide field of view, allowing astronomers to scan the sky efficiently. 2 competing teams, led by Batygin and Brown on one side, and astronomers Chad Trujillo and Scott Shepard on the other, are collaborating in the search. They anticipate that it could take up to 5 years to systematically explore the planet's possible locations. Initially, Batagin and Brown narrowed down the search region to an area spanning about 2,000 square degrees of sky, concentrated near the constellation Orion. They estimated that the Subaru telescope could cover this entire region in approximately 20 nights. With further refinements to their models, they have since reduced the search area to a much smaller zone of between 600 and 800 square degrees. In December of the year 2018, they dedicated several nights of observation time to the search, but the planet remained out of reach. Given the extreme difficulty in locating this hypothetical world, scientists have proposed using alternative methods to detect it. Instead of relying solely on ground-based telescopes, some researchers have suggested deploying multiple spacecraft to scan different parts of the sky from space. In late April and early May of the year 2020, scientists Scott Lawrence and Zeev Rogozinski proposed that such a mission could overcome many of the limitations faced by Earth-based observatories. If Planet 9 does exist, it is expected to be extremely dim because it is so far from the Sun. However, its large size means that it still radiates heat left over from its formation. At its estimated temperature of 47 Kelvin, equivalent to negative 226.2 degrees Celsius or negative 375.1 degrees Fahrenheit, the planet would emit most of its energy in the infrared spectrum. Its apparent brightness in visible light would be around magnitude 21.7, meaning it would be nearly impossible to spot with ordinary telescopes. However, this thermal radiation might be detected by advanced sub-millimeter telescopes, such as the Atacama Large Millimeter Sub-Millimeter Array, known as ALMA. Other astronomers have proposed that specialized cosmic microwave background experiments, which observe the sky at millimeter wavelengths, could also contribute to the search. A partial scan of the sky using archived data from the Atacama Cosmology Telescope has so far found no evidence of Planet 9. Nonetheless, Jim Green, a senior scientist at NASA, remains optimistic that the planet could be detected by the James Webb Space Telescope, the successor to the Hubble Space Telescope. Beyond professional astronomy, the search for Planet 9 has also extended to citizen scientists. NASA has launched a project called Planet 9 through the Zooniverse web portal, which invites the public to help analyze astronomical data. The project is not only looking for the hidden planet, but also aims to discover new brown dwarfs, faint, star-like objects that are smaller than normal stars. Some of these brown dwarfs may be among the closest celestial neighbors to our solar system. The initiative is led by Mark Kuchner, an astrophysicist at NASA's Goddard Space Flight Center. The Zooniverse Catalina Outer Solar System Survey was an exciting project that ran for almost 3 years, from August 2020 to April 2023. Scientists used old data from the Catalina Sky Survey to look for hidden celestial objects beyond Neptune, known as trans-Neptunian objects, TNOs. One of the biggest mysteries in space science is the possible existence of Planet 9, a giant planet that some researchers believe lurks far beyond Pluto. Precise calculations based on Saturn's orbit using data from the Cassini spacecraft suggest that if Planet 9 exists, it cannot be in certain parts of its predicted path. If it were, its gravitational pull would have noticeably shifted Saturn's position. However, these findings neither confirm nor completely rule out Planet 9's existence. A group of astronomers, Fienga, Lascar, Mancha, and Gastineau, analyzed data from Cassini to look for small differences in Saturn's expected orbit, which could hint at Planet 9's location. Their findings ruled out certain positions for the planet, but suggested it could be at a specific point in its orbit, about 630 times the Earth's distance from the Sun. If this is correct, Planet 9 would be found near the constellation Cetus, a region of the sky known for its mysterious deep space objects. A later study by astrophysicists Matthew Holman and Matthew Payne took this research even further. They developed a better model to analyze Cassini's data and explored a wider range of possible locations for Planet 9. Their calculations suggested that Planet 9 is most likely to be found near a spot in the sky close to 20 degrees from a specific right ascension, a celestial coordinate, once again pointing toward the Cetus constellation. Not all scientists agree on these theories. William Faulkner, a planetary expert at NASA's Jet Propulsion Laboratory, stated that Cassini never recorded any strange changes in its orbit around Saturn. If an unknown planet were out there, it should have affected Saturn's movement in a way that Cassini would detect. But no such disturbances were found in the data. In 2016, another analysis by Holman and Payne examined Pluto's orbit and found unexpected deviations, much larger than what would be expected if Planet 9 existed according to previous models. They proposed three possibilities. Errors in Pluto's orbit measurements could have led to incorrect conclusions. There might be an unknown mass in the solar system, possibly a smaller hidden planet at a distance of about 60 to 100 times Earth's distance from the Sun. Instead of the predicted Planet 9, there could be a different planet, either bigger or closer to the Sun than previously thought. Adding another layer to the mystery, a study of comets with unusual stretched-out orbits found 5 comets that seem to be moving in ways that match the predicted path of Planet 9. If these comets were disturbed by Planet 9's gravity, the planet would likely be near the farthest point in its orbit, in a specific range of celestial coordinates. However, Scott Shepherd, a well-known astronomer, remains skeptical, pointing out that many different forces could affect how comets move. Meanwhile, researchers Malena Rice and Gregory Laughlin proposed a new way to track Planet 9. They suggested setting up a network of telescopes to carefully observe how Jupiter Trojans, asteroids that share Jupiter's orbit, pass in front of distant stars. By studying the timing of these events, scientists might detect tiny shifts in the Trojans' orbits, possibly caused by the gravitational influence of Planet 9. In May 2022, another surprising theory emerged. Scientists suggested that an unusual meteor named Cineos 2014-0108 may have passed close to Planet 9 before entering an orbit that eventually brought it to Earth. If this idea is correct, then backtracking its path through space could reveal that Planet 9 is currently hiding in the constellation Aries. Yet another piece of evidence comes from studying distant icy objects beyond Neptune, known as extreme trans-Neptunian objects, ETNOs. Astronomers Sarah Milholland and Gregory Laughlin noticed a pattern in their orbits that suggests these objects might be locked in gravitational harmony with Planet 9. If this is true, it means Planet 9 could have a semi-major axis of about 654 times Earth's distance from the Sun and follow an orbit different from what was originally proposed. Other astronomers, Carlos and Raúl de la Fuente Marcos, also found similar patterns in the orbits of known ETNOs. Their analysis suggested that if an unknown planet exists, it could be positioned around 700 times Earth's distance from the Sun. Even smaller celestial bodies, such as 3 specific objects with semi-major axes near 172 times Earth's distance from the Sun, have been proposed as potential clues. If they are indeed being influenced by Planet 9, this could either mean that Planet 9 is located at a much closer distance than originally thought, around 315 times Earth's distance from the Sun, or that it follows an unusual orbit that allows their paths to move freely. A later study by Elizabeth Bailey, Michael Brown, and Konstantin Batygin found that if Planet 9 has an eccentric and tilted orbit, it could be pulling ETNOs into higher-order resonances. However, this chaotic behavior makes it very difficult to pinpoint Planet 9's exact orbit using current data. They also calculated that the chance of the first 6 observed ETNOs being in the expected pattern by coincidence is less than 5%, suggesting that something is truly influencing their movements. In 2025, a groundbreaking study by Amir Siraj, Christopher Chiber, and Scott Tremaine took a fresh look at the data using a sample of 51 ETNOs. They ran 300 computer simulations to estimate Planet 9's possible orbit. Their results suggested that Planet 9 might have a semi-major axis of around 290 times Earth's distance from the Sun, with a moderate orbital eccentricity and slight tilt. If this is correct, the mysterious planet could soon come into view through the powerful Rubin Observatory. Adding to the mystery, astronomers also discovered an exoplanet called HD 106-906b, which orbits a distant pair of stars in a highly stretched-out path. Interestingly, this exoplanet's orbit closely resembles what some scientists predict for Planet 9. While this distant planet is over 10 times the mass of Jupiter, studying it might help researchers understand how large planets can end up in such extreme orbits. Planet 9 does not yet have an official name, and it will not receive one unless scientists confirm its existence through actual images. So far, only 2 planets, Uranus and Neptune, have been discovered in recorded history. However, many smaller celestial objects, such as dwarf planets like Pluto, asteroids, and comets, have been identified and named over time. Because of this, there is already a well-organized system for naming newly found objects in our solar system. If Planet 9 is ever officially spotted, the International Astronomical Union will be responsible for approving its name. Normally, the people who discover a new celestial body get to suggest a name, and these names are often inspired by figures from ancient Roman or Greek mythology. When astronomers Konstantin Batygin and Mike Brown first introduced their idea about Planet 9, they simply called it Perturba, because they believed it was causing strange movements in other celestial bodies. Later, as their research gained attention, they started calling it Planet 9 in public discussions. Over time, they jokingly referred to it using different names, including Jehoshaphat and George, the latter being a reference to astronomer William Herschel's original attempt to name Uranus after a British king. Brown even admitted that among themselves they sometimes called it Fatty for fun. In the year 2018, Batygin playfully suggested naming the planet after the famous musician David Bowie. He also proposed that if the planet had any moons, they could be named after characters from Bowie's songs, such as Ziggy Stardust and Major Tom. The name Planet 9 has also been the subject of jokes. Many people have drawn a connection between it and the cult classic science fiction horror movie Plan 9 from Outer Space, directed by Ed Wood in the year 1959. This playful association even made its way into academic discussions. For instance, in the year 2016, Scientific American published an article titled Planet 9 from Outer Space, and since then, several scientific presentations have used the same wordplay. Astronomer Mike Brown even gave a lecture in the year 2019 with that title. Before the idea of Planet 9, many science fiction stories had imagined a distant planet beyond Neptune and often called it Persephone, the name of the goddess who was married to Pluto. Writers like Arthur C. Clarke and Larry Niven used this name in their books. However, if Planet 9 is ever confirmed, it is unlikely to be named Persephone because an asteroid, number 399, already has that name. Over the years, scientists have suggested other names for the mysterious planet. In the year 2017, physicist Lorenzo Iorio proposed calling it Tellisto, a word from ancient Greek that means the farthest or the most remote. Another idea came from physicist Makan Mohageg, who works at NASA's Jet Propulsion Laboratory. He suggested the name Kronos, after the Greek figure who represents time, since his proposed method for detecting Planet 9 involves extremely precise time measurements. Not everyone agrees with calling it Planet 9. In the year 2018, planetary scientist Alan Stern strongly objected to the name, saying that it disrespects Clyde Tombaugh, the astronomer who discovered Pluto. Stern argued that the name Planet X should be used until the object is actually found. He and 34 other scientists even signed a statement urging people to stop using Planet 9, and instead used neutral names like Planet X, Planet Next, or Giant Planet 5. Meanwhile, Mike Brown has explained why he does not think Planet X is a suitable name. He pointed out that the term Planet X originally referred to a specific prediction made by astronomer Percival Lowell, which eventually led to the discovery of Pluto, though by accident. Since his own research on Planet 9 is completely separate from that earlier idea, he believes a different name should be used. Saturn is famous for having the biggest and most complicated ring system of any planet in our solar system. These rings are made up of countless tiny particles that circle around the planet. Most of these particles are frozen water with only a tiny amount of rocky material mixed in. The size of these particles varies greatly. Some are as small as dust specks, while others are as large as houses. Scientists are still unsure about how Saturn's rings originally formed. Some theories suggest they have been around since the early days of the solar system, while data from NASA's Cassini spacecraft hints that they might have appeared much more recently. In the 9th month of the year 2023, astronomers proposed a new idea that Saturn's rings may have been created when two of its moons crashed into each other hundreds of millions of years ago. Even though Saturn's rings make the planet look brighter, they are too faint to be seen from Earth without a telescope. The first person to observe them was Galileo Galilei in the year 1610, just 1 year after he first pointed his telescope toward the heavens. However, because telescopes at the time were not very powerful, Galileo could not clearly see what he was looking at. He described Saturn as having ears, or appearing as three objects close together. It wasn't until the year 1655 that a Dutch astronomer named Christian Huygens correctly described them as a thin, flat disk surrounding the planet. The rings of Saturn are not one solid piece, but are instead made up of many smaller ring sections, separated by gaps. Some of these gaps exist because Saturn's moons disturb the movement of the ring particles, while others remain a mystery. Some rings, like the Titan ringlet and the G-ring, have remained stable for long periods because of gravitational forces that help keep them in place. One of the most distant rings, called the Phoebe ring, is believed to have come from a moon named Phoebe and moves in the opposite direction compared to the other rings. Galileo was fascinated by Saturn's rings, but struggled to understand them. In the year 1612, the rings temporarily disappeared from view when Earth passed through their plane, leaving him puzzled. He even wrote about the Greek myth of the Titan Saturn eating his own children, wondering if something strange had happened to the planet. When the rings reappeared in the year 1613, he remained confused about their true nature. In those early days of astronomy, scientists sometimes used secret codes or anagrams to claim discoveries before publishing them. Galileo used a scrambled Latin phrase to hint at his discovery of Saturn's rings before he was ready to reveal it. By the year 1657, an English scientist named Christopher Wren, who later became a famous architect, was studying Saturn's appearance. He came close to figuring out that the planet had a ring, but wasn't sure if it was attached to Saturn or floating separately. Before Wren could publish his ideas, Christian Huygens presented his own explanation, which was much more accurate. Realizing that Huygens was correct, Wren abandoned his work on the subject. Another scientist, Robert Hooke, also studied Saturn and noticed how the planet's rings cast shadows, giving clues about their structure. Meanwhile, Huygens had been carefully designing telescopes with his father and, in the year 1655, used one with 43 times magnification to observe Saturn in detail. He became the first person to suggest that Saturn was surrounded by a thin, flat ring that did not touch the planet itself. To keep his discovery secret until he was ready to publish, he wrote a long, seemingly random string of letters, which he later revealed to mean, "Saturn is surrounded by a thin, flat ring, nowhere touching the planet and tilted with respect to the sun." 3 years later, Huygens officially published his findings in a book called Systema Saturnium, which not only described the rings, but also included his discovery of Saturn's largest moon, Titan. His work provided one of the first accurate measurements of our solar system's size. In the year 1675, another astronomer, Giovanni Domenico Cassini, discovered that Saturn's rings were actually made up of multiple smaller rings separated by gaps. The largest of these gaps, which spans nearly 4,800 kilometers, or about 3,000 miles, was later named the Cassini division in his honor. More than a century later, in the year 1787, a French mathematician named Pierre-Simon Laplace proved that a solid, unbroken ring around Saturn would be unstable and eventually fall apart. Instead, he suggested that the rings were made up of countless small ringlets. His idea turned out to be correct, and today, scientists know that Saturn's rings are not a single solid structure, but rather a vast collection of tiny particles, each following its own orbit around the planet. In the year 1859, the brilliant Scottish physicist James Clerk Maxwell made an astonishing discovery about Saturn's rings. He showed that if the rings were made of a single solid structure, uneven ringlets, or even a continuous band of liquid, they would not remain stable. This meant that Saturn's rings had to be made up of countless small particles, each moving independently around the planet in its own orbit. Later, the gifted Russian mathematician Sofia Kovalevskaya confirmed that Saturn's rings could not be liquid structures either. This idea was proven true decades later through the power of spectroscopy, a technique that analyzes light to determine the composition and movement of objects. In the year 1895, two astronomers, James Keeler from Allegheny Observatory and Aristarch Belopolsky from Pulkovo Observatory, independently studied Saturn's rings. Their findings matched Maxwell's predictions, proving once and for all that the rings were composed of countless small particles rather than being a solid or liquid mass. Saturn's rings have been observed up close by 4 robotic spacecraft, each of which provided breathtaking insights into this mesmerizing system. The first was Pioneer 11, which came closest to Saturn in September of the year 1979, passing within 20,900 kilometers or 13,000 miles of the planet. This mission led to the discovery of the mysterious F-ring. Then, Voyager 1 made its closest approach in November of the year 1980 at a distance of 64,200 kilometers or 39,900 miles. Unfortunately, a malfunctioning instrument prevented it from capturing images of the rings in high resolution. Still, it managed to provide stunning photographs, revealing the presence of a previously unknown ring, the G-ring. A year later, in August of 1981, Voyager 2 arrived, coming within 41,000 kilometers or 25,000 miles of Saturn. Unlike its predecessor, Voyager 2 had a functioning photopolarimeter which allowed it to capture sharper, more detailed images of the rings. Thanks to this, astronomers discovered many previously unseen ringlets. Finally, in July of the year 2004, the Cassini spacecraft entered Saturn's orbit. Cassini provided the most detailed images of the rings ever seen and revealed even more delicate structures within them. Saturn's rings have been named in the order they were discovered rather than their actual position around the planet. The first two, the A and B rings, were spotted in the year 1675 by astronomer Giovanni Domenico Cassini. The C ring was found in the year 1850 by William Cranch Bond and his son, George Phillips Bond. The D ring was identified in the year 1933 by Nikolai Barabashov and Boris Semakin. The E ring was added in the year 1967 by Walter Feibelman, followed by the F ring in 1979 thanks to Pioneer 11. Finally, the G ring was found in 1980 by Voyager 1. Looking at Saturn's rings from the planet outward, the major ones are the C, B, and A rings, separated by a large gap known as the Cassini division. Beyond these, several fainter rings exist. The closest to Saturn is the barely visible D ring. The narrow F ring sits just beyond the A ring, and even farther out are the faint G and E rings. The structure of the rings is incredibly complex, influenced by Saturn's moons and other factors that scientists have yet to fully understand. In September of the year 2023, astronomers put forward a fascinating theory about how Saturn's rings may have formed. According to their research, the rings might be the result of a catastrophic collision between two moons hundreds of millions of years ago. Saturn is tilted on its axis at an angle of 26.7 degrees, which means that from Earth, our view of its rings changes over time. Every 13 to 15 years, about half of a Saturnian year, Earth passes through the ring plane, causing the rings to appear nearly invisible. This last happened on the 22nd of May in the year 1995, the 10th of August in 1995, the 11th of February in 1996, and the 4th of September in the year 2009. The next such event will occur on the 23rd of March in the year 2025, followed by more in the years 2038 and 2039. The best times to view the rings during these events are when there are 3 crossings in a row rather than just one. Saturn's equinoxes, when the Sun passes through the plane of the rings, do not occur at equal intervals. When Saturn reaches a heliocentric longitude of 173.6 degrees, the Sun moves from the southern side of the rings to the northern side. This last happened on the 11th of August in the year 2009. About 15.7 years later, when Saturn reaches 353.6 degrees, the Sun moves back to the southern side. This means that during each of Saturn's orbits, the Sun shines on the northern side of the rings for 15.7 Earth years, then on the southern side for 13.7 years. The most recent north-to-south transition happened on the 19th of November in the year 1995, and the next will occur on the 6th of May in the year 2025. Meanwhile, the next south-to-north transition will take place on the 23rd of January in the year 2039. Around the time of an equinox, the rings become much less illuminated, allowing astronomers to study features that normally remain hidden. Saturn's main rings extend from 7,000 kilometers, or 4,300 miles, to 80,000 kilometers, or 50,000 miles, away from the planet's equator. For reference, Saturn's equatorial radius itself is about 60,300 kilometers, or 37,500 miles. These rings are astonishingly thin compared to their vast width. In some places, they are only 10 meters, or 32 feet 10 inches, thick, while in others, they can reach a thickness of 1 kilometer, or 1,093 yards. They are made up almost entirely of frozen water, with tiny traces of other materials, such as silicates or complex organic compounds called tholins. Most of the ring particles are smaller than 10 meters across. During its final orbits, Cassini measured the mass of the rings by studying their gravitational pull. Scientists determined that the total mass of the rings is about 1.54 times 10 to the power of 19 kilograms. To put this in perspective, that is around 2/3 the mass of all the ice in Antarctica, but spread across an area 80 times larger than Earth's surface. This measurement closely matched earlier calculations based on density waves within the A, B, and C rings. Despite their enormous appearance, the rings contain only a tiny fraction of Saturn's total mass, about 0.25 parts per billion. Earlier studies from the Voyager spacecraft had underestimated their mass, but later observations and computer models provided a more accurate picture. Saturn's rings, some of the most stunning features in our solar system, are far more complex than they appear. While the largest gaps within the rings, such as the Cassini division and the Encke gap, can be spotted even from Earth. It was NASA's Voyager spacecraft that revealed a breathtaking level of detail. It discovered that Saturn's rings contain thousands of delicate gaps and thin ringlets, forming an intricate, almost lace-like structure. Scientists believe this mesmerizing pattern is shaped by the gravitational influence of Saturn's numerous moons in several different ways. Some gaps in the rings are cleared by tiny moonlets, like Pan, which orbits within the Encke gap. Many more such moonlets may still be waiting to be discovered. Other thin rings and gaps seem to be shaped and maintained by small moons known as shepherd satellites, much like how Prometheus and Pandora help structure the F-ring. Another fascinating phenomenon influencing the rings is the gravitational pull of Saturn's larger moons, such as Mimas. When the particles within the rings orbit at specific speeds that match the movement of a larger moon further away, their paths become unstable, creating gaps like the Cassini division. Meanwhile, some sections of the rings form graceful spiral waves due to the rhythmic tug of Saturn's inner moons, which slightly disturb the ring particles in a repeating pattern. One of the most astonishing discoveries made by NASA's Cassini probe was that Saturn's rings have their own atmosphere, entirely separate from the planets. This delicate atmosphere is made primarily of molecular oxygen, which forms when sunlight interacts with the ice within the rings, breaking apart water molecules. The resulting fragments go through chemical reactions, producing oxygen gas and even hydrogen. However, this atmosphere is incredibly thin, so sparse that if it were to settle onto the rings as a solid layer, it would be no thicker than a single atom. There is also a faint presence of hydroxide, OH, which forms when high-energy particles strike water molecules ejected from Saturn's moon, Enceladus. Incredibly, this ghostly atmosphere was detected from Earth using the Hubble Space Telescope. Saturn itself undergoes fascinating changes in brightness over time. The biggest factor behind this variation is the shifting angle of the rings as the planet orbits the Sun. Over the course of its nearly 30-year journey around our star, the rings tilt and present different perspectives to Earth, making Saturn appear brighter or dimmer. Additionally, the planet's slightly oval-shaped orbit causes another subtle change in brightness, with the northern hemisphere appearing slightly more brilliant when it faces the Sun compared to the southern hemisphere. One of the most remarkable moments in the exploration of Saturn's rings came in the year 1980, when Voyager 1 flew past the planet and captured images of the mysterious F-ring. At first glance, this ring seemed to be made up of 3 strands that appeared to be braided together in a complex weave. However, later analysis showed that this illusion was caused by clumps, twists, and irregularities in 2 of the outermost rings, while a third, dimmer ring lay inside them. More recent images taken by NASA's Cassini spacecraft during Saturn's equinox on the 11th of August, 2009 provided another surprise. They revealed that in certain places, Saturn's rings extend significantly above and below the usual flat plane. This unusual displacement is most striking at the edge of the Keeler Gap, where a small moon called Daphnis orbits in a slightly tilted path, pulling ring particles up and down as it moves. In some areas, this effect causes the rings to rise as much as 4 kilometers, or about 2.5 miles, above their expected position. The question of how old Saturn's rings are remains one of the biggest mysteries in planetary science. Some theories suggest that the rings are incredibly ancient, possibly forming at the same time as Saturn itself, more than 4 billion years ago. However, data from the Cassini probe challenges this idea. According to recent estimates, the rings might be much younger, perhaps only between 10 million and 100 million years old. If this is correct, they may have appeared relatively recently in cosmic history, long after the age of the dinosaurs on Earth. Scientists arrived at this conclusion by studying how the rings evolve over time. Since they constantly lose material due to collisions and dust accumulation, the rings must have been much more massive in the past. Based on current loss rates, calculations suggest that Saturn's rings might completely disappear in another 300 million years, leaving only a faint, dusty remnant. As for the origin of these majestic rings, scientists have proposed two main possibilities. The first idea, first suggested by the French astronomer Édouard Roche in the 19th century, is that the rings were once a moon of Saturn. This hypothetical moon, which some researchers have nicknamed Chrysalis, may have moved too close to Saturn and been torn apart by the planet's immense gravitational forces. Recent computer simulations from the year 2022 support this theory, showing that a moon could have broken apart in this way, scattering its icy remains into orbit around Saturn. Another version of this hypothesis suggests that the moon may have been shattered by a collision with a large comet or asteroid. The second theory is that Saturn's rings were never part of a moon at all. Instead, they may be leftover material from the original cloud of gas and dust that formed Saturn billions of years ago. A more detailed version of the disrupted moon hypothesis suggests that the rings could be the remains of a moon that was about 400 to 600 kilometers, or about 200 to 400 miles, in diameter, slightly larger than Saturn's current moon, Mimas. If this is the case, then the event that created the rings may have occurred around 4 billion years ago, during a violent period in the solar system's history known as the Late Heavy Bombardment, when planets and moons were frequently struck by large space debris. Another variation of this idea, proposed by planetary scientist R.M. Canup, suggests that the rings might be the outer shell of a much larger moon, possibly one as big as Saturn's largest moon, Titan. In this scenario, the moon was stripped of its icy outer layers as it spiraled into Saturn during the early days of the solar system. This could explain why the rings contain very little rocky material and are made mostly of ice. In their early stages, the rings would have been far more massive and extended much farther from the planet. Over time, material from the outer edges of the rings may have come together to form Saturn's inner moons, such as Tethys. Interestingly, this theory might also explain certain peculiarities of Saturn's moon, Enceladus. Unlike its neighboring moons, Enceladus has a relatively high density, suggesting that it lost a significant amount of ice at some point in its past. This could have happened due to later collisions or volcanic activity, causing it to evolve into its current state. Scientists believe that Saturn once had massive rings that played a key role in shaping its moons, particularly out to rear. If these early rings were made of both ice and rocky chunks larger than 100 kilometers, 60 miles across, the heavier rocky pieces would have gradually collected more ice. Over time, due to the effects of Saturn's gravity and the pull of the rings, these growing bodies would have been pushed outward into wider orbits, eventually forming moons. Within a certain distance from Saturn, known as the Roche limit, rocky objects were dense enough to continue gathering material, while icy bodies remained fragile and could not do the same. Once these developing moons escaped from the rings, they might have continued to grow through random collisions and mergers with other space debris. This theory could explain why Saturn's moons have varying amounts of rock, with those farther from the planet containing more silicate material and those closer having less. Based on this, Rhea would be the oldest of these moons, while those orbiting closer to Saturn would have formed more recently. Another mystery surrounding Saturn's rings is their striking brightness and purity, which suggests they might be much younger than the planet itself. Over billions of years, space dust from meteors should have darkened the rings, yet they remain relatively clean. Scientists have found that the B ring, one of Saturn's largest, may be massive enough to dilute the incoming dust, preventing it from significantly darkening over time. Additionally, the rings seem to recycle material. Clumps of ice form within them, only to be broken apart by impacts, constantly renewing their appearance and giving the illusion that they are younger than they truly are. Recent studies suggest that the C ring might be even younger than previously thought. Data from the Cassini-Titan radar mapper indicate that this ring contains a significant amount of rocky material. If this material came from a moon or centaur, a type of icy asteroid that was recently destroyed, the C-ring might be as young as 100 million years. However, if the material primarily came from tiny space rocks gradually accumulating over time, it could be as old as 1 billion years. In another fascinating discovery, the Cassini-Uvis team, led by Larry Esposito, used a technique called stellar occultation to detect 13 objects within Saturn's F-ring. These objects ranged in size from 27 meters, 89 feet, to 10 kilometers, 6 miles, across. They appeared translucent, meaning they were likely clusters of ice boulders held loosely together. Esposito believes this constant clumping and breaking apart is a fundamental characteristic of Saturn's rings. One major question scientists are trying to answer is how long Saturn's rings will last. Research suggests they may only exist for hundreds of millions of years. Material from the rings is continuously spiraling down into Saturn, a process influenced by the planet's magnetic field. This ring rain pulls electrically charged ice grains into Saturn's atmosphere, gradually eroding the rings. Observations from the Keck telescope estimate that this process causes between 432 and 2,870 kilograms of material to fall into Saturn every second. Based on this rate alone, Saturn's rings could vanish in approximately 300 million years. However, when the Cassini spacecraft traveled between Saturn and its rings in September 2017, it detected an even more significant influx of material, between 4,800 and 44,000 kilograms per second. If this rate remains steady, Saturn's rings could disappear in less than 100 million years. Saturn's main rings are the A and B rings, separated by a dark gap called the Cassini division, which was discovered in 1675 by the astronomer Giovanni Domenico Cassini. The C-ring, found in 1850, is similar in nature to the Cassini division. These three make up the densest parts of Saturn's ring system and contain larger particles. In contrast, Saturn also has fainter, more diffuse rings made up of tiny dust particles, including the D-ring, which extends closest to the planet, the G-ring, and the E-ring. These rings are primarily made of water ice, just like the main rings, but their particles are much smaller. The F-ring, located just beyond the A-ring, is unique because parts of it are dense, while other sections are filled with tiny dust-sized particles. The D-ring is the closest to Saturn and is very faint. In 1980, the Voyager 1 spacecraft identified 3 thin rings within this region, named D73, D72, and D68. The closest of these, D68, remains the most well-defined. However, by the time the Cassini spacecraft observed the area 25 years later, D72 had become much broader and more diffuse and had moved about 200 kilometers, 100 miles, closer to Saturn. One of the most intriguing features within the D-ring is a fine wave-like structure with crests about 30 kilometers, 20 miles, apart. Scientists first noticed these waves in the gap between the C-ring and D73. By the time of Saturn's equinox in 2009, researchers discovered that the pattern extended across a vast distance of 19,000 kilometers, 12,000 miles, reaching all the way to the inner edge of the B-ring. These waves appear to be part of a spiraling pattern of vertical ripples, varying in height from 2 to 20 meters, 6 to 60 feet. The fact that the distance between the waves is decreasing over time suggests that this pattern was created in the early 1980s by the impact of a massive cloud of debris. This debris likely came from a disrupted comet which tilted the rings slightly out of alignment. A similar spiraling effect has been observed in Jupiter's main ring, which scientists believe was caused by the impact of material from Comet Shoemaker-Levy 9 in 1994. The C-ring is a broad yet faint ring located closer to Saturn than the brighter B-ring. It was first spotted in the year 1850 by astronomers William Bond and his son George Bond. However, other astronomers, including William Dawes and Johann Galle, also observed it independently around the same time. Another astronomer, William Lassell, gave it the nickname crepe ring because it appeared to be made of darker material compared to the much brighter A and B rings. This ring is surprisingly thin, with an estimated vertical thickness of about 5 meters, which is roughly 16 feet. Despite its vast size, the ring itself is not very dense. Scientists estimate its mass to be approximately 1.1 quintillion kilograms. The ring's transparency varies. It blocks only about 5 to 12% of the light that shines directly through it, which means that if you were to look at it from above, it would seem almost invisible. Interestingly, in the year 2009, during Saturn's equinox, scientists discovered that a type of wave-like pattern called spiral corrugations, originally found in the even fainter D-ring, extended into the C-ring as well. Within the inner part of the C-ring, there is a gap known as the Colombo Gap. This narrow region contains a thin but bright ringlet called the Colombo ringlet, which is also known as the Titan ringlet. It lies at a distance of 77,883 kilometers, or about 48,394 miles, from the center of Saturn. Unlike most rings, which are perfectly circular, this ringlet is slightly elliptical. Its shape and position are controlled by the gravitational pull of Saturn's largest moon, Titan. The effect is so precise that the outermost part of the ringlet is always aligned with Titan's position in orbit. Another gap in the C-ring is called the Maxwell Gap, which contains a dense and unusual ringlet known as the Maxwell ringlet. This ringlet is not circular and has strange wave-like structures running through its middle. In some ways, it resembles the narrow Epsilon ring of Uranus. On Uranus, the waves in the Epsilon ring are believed to be caused by the small moon Cordelia. But for Saturn's Maxwell Gap, no such moon has been discovered, at least not as of July 2008. Now, moving to the B-ring, the most massive, brightest, and largest of all Saturn's rings. Its thickness varies between 5 and 15 meters, and in some places it is so dense that it blocks more than 99% of any light trying to pass through it. Unlike the C-ring, the B-ring has an enormous variety of density patterns and brightness levels, forming many narrow bands. Despite decades of research, scientists still do not fully understand why these variations exist. The outer edge of the B-ring is even more fascinating. In some regions, the ring is not flat, but has towering structures that rise up to 2.5 kilometers, about 1.5 miles, above the ring plane. This is extraordinary when you consider that most of Saturn's rings are only about 10 meters, or 30 feet, thick. Scientists believe these towering features might be caused by small, hidden moonlets embedded within the ring material. A study conducted in the year 2016 used a technique called stellar occultation to analyze spiral density waves in the B-ring. The findings revealed that the surface density of the ring ranged between 40 and 140 grams per square centimeter, which was surprisingly lower than what had been previously assumed. Another unexpected discovery was that the ring's optical depth, how much light it blocks, did not necessarily match its mass density. This phenomenon had also been noticed in Saturn's A and C rings. Researchers estimated that the total mass of the B ring was somewhere between 7 and 24 quintillion kilograms, which is much smaller than Saturn's moon Mimas, which has a mass of about 37.5 quintillion kilograms. For a long time, scientists believed Saturn's rings were shaped solely by gravitational forces. However, in the year 1980, NASA's Voyager spacecraft sent back images of strange, shadowy streaks appearing across the B-ring. These streaks, which scientists call spokes, were unlike anything seen before. They rotated around Saturn's rings but did not behave the way gravitational forces predicted. When viewed from different angles, they appeared dark when sunlight hit them from behind, but bright when light shined through them from the front. The leading theory is that these spokes are made of tiny dust particles that become electrically charged and get lifted above the main ring by Saturn's magnetic field. However, the exact reason for their formation remains a mystery. Some researchers have suggested that the spokes might be caused by lightning discharges in Saturn's atmosphere, while others believe they could be the result of tiny meteoroids colliding with the rings. Another idea is that they resemble the lunar horizon glow seen on the Moon, where electrostatic forces push dust particles away from the surface. After the Voyager mission, the spokes mysteriously vanished for nearly 25 years. Then, in September 2005, NASA's Cassini spacecraft finally detected them again. Interestingly, the spokes seem to be seasonal. They disappeared during Saturn's summer and winter, but returned as the planet approached its equinox, which happens once every 29.7 Earth years. Observations from Cassini over the years confirmed that these strange features gradually became more visible as the equinox approached. In 2009, during Saturn's equinox, Cassini made another astonishing discovery: a tiny moonlet hidden within the E-ring. Scientists spotted it by the shadow it cast on the rings. This moonlet was estimated to be about 400 meters, or 1,300 feet, across, and was given the temporary name S/2009 S1. Another key feature of Saturn's rings is the Cassini division, a massive gap measuring about 4,800 kilometers, or roughly 3,000 miles, in width. It separates the A-ring from the B-ring and appears as a thin black line when viewed from Earth. This division was first discovered in the year 1675 by astronomer Giovanni Cassini, using a telescope with a magnification power of 90 times. For centuries, astronomers believed this gap was empty, but when the Voyager spacecraft passed by, it revealed that the Cassini division actually contains ring material similar to that found in the C-ring. Although this region may seem dark from Earth, it can appear bright when viewed from the side of the rings that faces away from the Sun. This is because the sparse ring particles allow light to pass through, creating a glowing effect when seen against the blackness of space. The inner edge of Saturn's Cassini division is influenced by a powerful gravitational effect called orbital resonance. This happens because the tiny ice and rock particles in this region complete 2 full orbits around Saturn for every single orbit of the moon Mimas. Over time, Mimas's gravitational pull keeps tugging at these particles in a way that throws their movement off balance, causing their orbits to become unstable. This constant disturbance clears out much of the material, creating a sharp boundary in the ring system. However, while scientists understand why this particular gap exists, many of the other empty spaces within the Cassini division remain a mystery. In the year 1981, the Voyager 2 spacecraft sent back images revealing a fascinating feature at the inner edge of the Cassini division, an area known as the Huygens Gap. Sitting right in the middle of this gap is a ringlet called the Huygens ringlet, which is unusually dense and follows an eccentric or slightly oval path around Saturn. Scientists have noticed that this ringlet changes in width and brightness in irregular ways. They believe these variations might be caused by the gravitational influence of Mimas, which interacts with the ringlet in a 2-to-1 resonance, meaning Mimas completes 1 orbit for every 2 orbits of the ringlet's particles. Another possibility is that the shifting outer edge of Saturn's massive B-ring also plays a role in shaping these irregular patterns. Outside the Huygens ringlet, there is yet another, much thinner ringlet. The A-ring is the widest and brightest of Saturn's main rings. It stretches from the Cassini division on its inner side all the way out to a point near the orbit of a tiny moon called Atlas. However, the A-ring is not a continuous, unbroken band. It has a major break within it, known as the Encke gap, which is located about 22% of the way from its outer edge. There is also a second, much narrower gap, called the Keeler gap, sitting only about 2% from the outer boundary. The thickness of the A-ring is estimated to be between 10 and 30 meters. Scientists believe that the amount of material packed into this ring is between 35 and 40 grams per square centimeter, and the total mass of the entire E-ring is between 4 and 5 quintillion kilograms. That's a number so huge, it's almost the same as the mass of Saturn's small moon Hyperion. The E-ring's transparency also varies, meaning some parts let more light through than others, with values ranging from 40% to 90%. Much like the neighboring B-ring, the outer edge of the E-ring is controlled by gravitational resonances. However, in this case, the interactions are more complex. The strongest influence comes from the moons Janus and Epimetheus, whose orbits create a 7-to-6 resonance with the E-ring. Additional disturbances come from the moon Mimas, which affects the ring through a 5-to-3 resonance, and from two other moons, Prometheus and Pandora, which add even more gravitational influences. These different forces generate countless spiral-shaped waves in the E-ring, much like the arms of a spiral galaxy. Some of these waves cause compression within the ring, while others create a vertical rippling effect, making the material rise and fall slightly as it orbits Saturn. In April of the year 2014, NASA scientists made a groundbreaking observation near the outer edge of the E-ring. They saw what looked like the formation of a brand new moon, a tiny object just beginning to take shape. This could be a glimpse into the birth of a future moon of Saturn. The Encke Gap, which is about 325 kilometers, 200 miles wide, sits within the E-ring at a distance of about 133,590 kilometers, 83,000 miles, from the center of Saturn. It exists because of the small moon Pan, which orbits within this gap, keeping it clear of ring material. High-resolution images captured by the Cassini spacecraft have shown that at least 3 thin, twisted ringlets still manage to exist within the gap. On both sides of the Encke Gap, there are spiral-shaped waves in the rings caused by gravitational influences from other moons further out. Meanwhile, Pan itself generates additional swirling patterns within the gap. Interestingly, Johann Encke, the astronomer for whom this gap is named, never actually saw it. Instead, it was discovered in the year 1888 by another astronomer, James Edward Keeler. Later, when the Voyager spacecraft found a second major gap in the E-ring, it was named the Keeler Gap in Keeler's honor. For many years, there was confusion over whether to call the Encke Gap a gap or a division. But in the year 2008, the International Astronomical Union officially clarified that a gap is a space entirely within a ring, while a division is a larger separation between different rings. The Keeler Gap is much smaller than the Encke Gap, measuring only 42 kilometers, 26 miles wide. It is located about 250 kilometers, 150 miles, from the outer edge of the E-ring. Inside this narrow gap orbits a tiny moon named Daphnis, which was discovered on May 1, 2005. Daphnis plays an important role in maintaining the gap. As it moves through the E-ring, its gravity pulls on the ring material at the edges, creating wave-like disturbances. Because Daphnis's orbit is slightly tilted, some of these waves actually rise above the flat plane of the rings, reaching heights of up to 1,500 meters, almost a mile, above the ring surface. In the year 2006, Cassini's cameras detected 4 tiny moonlets inside the E-ring. These objects are only about 100 meters, 300 feet, across, far too small to be seen directly. Instead, scientists noticed them because of the unusual propeller-shaped patterns they created in the surrounding ring material. Further observations in the year 2007 revealed 8 more moonlets, mostly concentrated in a belt about 3,000 kilometers, 2,000 miles wide, positioned 130,000 kilometers, 80,000 miles, from Saturn's center. By the year 2008, over 150 of these propeller moonlets had been detected, and one of them, which has been closely tracked for years, was even given the nickname Blériot. Beyond the E-ring lies a lesser-known gap called the Roche division, named in honor of the French physicist Édouard Roche. This division separates the A-ring from Saturn's thin and ghostly F-ring. The name might be confusing because Roche limit is also a scientific term referring to the distance at which a planet's gravity is strong enough to tear apart a large object. The Roche division is located near Saturn's Roche limit, which is why the ring material has never been able to come together to form a moon. Unlike the Cassini division, which is largely empty, the Roche division still contains some scattered ring material. Scientists have found that it is similar to Saturn's more diffuse rings, the D, E, and G rings. In two specific areas within the Roche division, there are higher concentrations of dust. These regions, first identified by the Cassini spacecraft, were given temporary names: R2004-S1, which follows the path of the small moon atlas, and R2004-S2, which is centered about 138,900 kilometers, 86,300 miles, from Saturn's center, just inside the orbit of the moon Prometheus. The outermost distinct ring of Saturn is the F-ring, which is one of the most dynamic and ever-changing rings in the entire solar system. Its appearance can change within just a few hours. It is positioned about 3,000 kilometers, 2,000 miles, beyond the A-ring's outer edge, and was first observed in the year 1979 by the Pioneer 11 spacecraft. The F-ring is incredibly thin, only a few hundred kilometers, miles wide. It was long believed that two moons, Prometheus and Pandora, acted as shepherds, keeping the ring in place. However, newer studies suggest that only Prometheus plays a major role in shaping the ring. Some scientists even think the ring may have formed after a collision between these two moons, causing material to spread out and create the F-ring as we see it today. Recent close-up images taken by the Cassini spacecraft have given us a much clearer look at Saturn's mysterious F-ring. These images reveal that the F-ring is not just a simple band of material. It actually consists of a main core ring with a delicate spiral strand wrapped around it. One of Saturn's small moons, Prometheus, plays a major role in shaping the F-ring. As Prometheus moves along its orbit and reaches its farthest point from Saturn, its gravity tugs at the particles in the ring. This interaction causes twists, knots, and dark gaps to form in the ring, almost as if the moon is stealing material from it. Since Prometheus orbits Saturn faster than the particles in the F-ring, each new dark gap appears slightly ahead of the previous one, at a difference of about 3 degrees. In the year 2008, scientists observed even more activity in the F-ring. It appeared that tiny, previously unseen moons were constantly passing through the narrow core of the ring, likely due to the gravitational influence of Prometheus. One such small moon, tentatively identified as S/2004-S6, was found among these dynamic interactions. By the year 2023, astronomers had pieced together a fascinating theory about the F-ring structure. It is now believed that thousands of small parent objects, ranging in size from about 1/10 of a kilometer to a full kilometer across, are continuously colliding and breaking apart. This process creates dense filaments of tiny particles, some no bigger than a grain of sand, while others are as large as a pebble. Over time, these particles drift back and reattach to the parent bodies, maintaining a delicate balance that keeps the ring in a steady state. The Cassini spacecraft, using a special technique to capture light scattered forward, also discovered a faint, dusty ring in the region where two of Saturn's moons, Janus and Epimetheus, orbit. This ring, spanning about 5,000 kilometers or 3,000 miles in width, is made up of tiny particles that have been knocked off the surfaces of these moons by constant collisions with micrometeoroids. As these particles are ejected, they spread out and form a thin, hazy ring along the paths of Janus and Epimetheus. Saturn's G-ring, located between the F-ring and the much larger E-ring, is one of the planet's more delicate rings. It is an extremely thin and faint structure, with its inner edge positioned about 15,000 kilometers or 10,000 miles inside the orbit of the moon Mimas. Within this ring, scientists have observed a brighter, more concentrated arc of material stretching across about 1/6 of the ring's circumference. This arc is centered around a tiny moonlet named Aegean, which is only about 500 yards in diameter. The arc remains stable due to a gravitational resonance with Mimas, meaning the larger moon's gravity helps keep the material confined in a specific region of the G-ring. The particles in the arc of the G-ring are believed to be made mostly of ice, some as small as grains of sand, while others may be a few meters across. The rest of the G-ring is composed of dust, likely released from within the arc itself. The arc is about 250 kilometers, or 150 miles, wide, while the entire G-ring spans a massive 9,000 kilometers, or 6,000 miles, in width. Scientists estimate that all the material in the arc adds up to about the same mass as a small, icy moonlet, measuring around 100 meters in diameter. Over time, tiny impacts from space debris cause dust to break away from Aegean and other bodies within the arc. This dust slowly drifts outward, influenced by Saturn's powerful magnetic field. The planet's magnetic environment, which rotates much faster than the G-ring's orbit, steadily pulls these fine particles away, eventually causing the ring to lose mass. However, each new impact on Aegean replenishes the supply of material, ensuring that the ring continues to exist. In September of 2006, astronomers made another discovery, a faint arc of material located near Saturn's small moon Methone. This arc stretches about 10 degrees in longitude and is thought to consist of dust particles knocked off Methone's surface by micrometeoroid impacts. The dust remains confined in this arc due to a gravitational resonance with Mimas, similar to what happens in the G-ring. Because of this resonance, Methone itself oscillates slightly in its orbit, shifting back and forth over an angle of 5 degrees. A similar arc was detected in June of 2007, this time near another moon named Anthe. This arc extends about 20 degrees in longitude and is also made up of dust particles that were likely dislodged by impacts from tiny meteoroids. Like Methone's arc, Anthe's dust remains trapped due to a gravitational resonance with Mimas. As a result, Anthe's orbit also shifts back and forth over an angle of about 14 degrees. Saturn's moon Pallene has its own faint dust ring, which was revealed in 2006 through Cassini's images. This ring stretches about 2,500 kilometers, or 1,500 miles, in width. Its origin is similar to the other dust rings. Tiny particles get blasted off Pallene's surface when meteoroids collide with it, and these particles then spread out to form a thin, diffuse ring along its orbital path. The E-ring, one of Saturn's most mysterious and debated rings, was not officially confirmed until the year 1980. However, astronomers had suspected its existence for decades. In fact, as early as the year 1908, astronomers like Georges Fournier and E. Scheer reported seeing a faint, hazy band surrounding Saturn's brighter rings. Over the next several years, other astronomers, including W. Boyer, T. Lewis, and Arthur Eddington, also made observations that suggested the presence of an additional ring. However, their findings were inconclusive, and when renowned astronomer Edward Barnard failed to detect the ring using the world's most advanced telescope at the time, skepticism about its existence grew. For decades, astronomers remained divided over whether the E-ring was real. Unlike Saturn's brighter A, B, and C rings, the E-ring is extremely faint and has a large vertical spread, making it difficult to observe except when viewed edge-on, a rare event that only occurs once every 14 to 15 years. The controversy resurfaced in the 1960s when Walter Feibelman published observations in the year 1966 that suggested the presence of an outer ring. However, even he acknowledged that his findings were tentative. Later, during the Pioneer 11 spacecraft's flyby of Saturn in the year 1979, instruments detected indirect evidence of a ring in that region, but no direct images could confirm it. It wasn't until the year 1980 that the existence of the E-ring was finally proven beyond doubt. A combination of reanalyzed observations from the 1960s, new telescope data, and space-based imaging confirmed that Saturn did, in fact, have this elusive, ghostly ring. Today, we know that the E-ring is unlike any other. It is composed mostly of tiny ice particles that are constantly replenished by Saturn's active moon Enceladus, which ejects plumes of water vapor and ice from its surface. The E-ring is the second farthest ring from Saturn and is incredibly vast. Unlike the planet's other rings, which are made up of large chunks of ice and rock, the E-ring is mostly composed of tiny dust-like particles, many of them smaller than the width of a human hair. These microscopic particles are primarily made of frozen water, but they also contain traces of silicates, carbon dioxide, and ammonia. The E-ring stretches across the space between the orbits of Saturn's moons Mimas and Titan. For a long time, scientists weren't sure where all this material came from. Then, in the year 2005, they made a breakthrough. They discovered that the particles in the E-ring are actually being ejected from Enceladus, one of Saturn's most fascinating moons. Enceladus has an icy surface, and from its south pole, massive geysers, known as cryovolcanic plumes, shoot water vapor and ice particles into space. These jets emerge from large cracks on Enceladus's surface called tiger stripes. Over time, this ejected material spreads out and forms the E-ring. Another unusual trait of this ring is its thickness. It is more than 2,000 kilometers, over 1,000 miles, thick. In fact, the farther you go from Enceladus, the thicker the ring becomes. Some parts of the E-ring even have tendril-like structures, which seem to match the movement of the strongest geysers erupting from Enceladus's south pole. Because the E-ring is so spread out, its tiny ice particles tend to stick to any nearby moons that pass through it. One example is Tethys, another of Saturn's moons. The leading side of Tethys has a faint blue tint because it collects so much material from the E-ring. Other smaller moons, such as Telesto, Calypso, Helene, and Polydeuces, are also affected. Since these moons move slightly above and below the main plane of the ring, they get continuously dusted with bright, icy particles, which slowly smooth out their surfaces over time. In October 2009, astronomers made an astonishing discovery: a gigantic ring made of thin, faint dust particles located near the orbit of Phoebe, one of Saturn's outermost moons. This enormous structure isn't like the bright rings we usually associate with Saturn because it is nearly invisible. However, when viewed using NASA's infrared Spitzer space telescope, it appeared as a massive, dim disk of material. At the time of its discovery, this ring was seen edge-on from Earth, making it difficult to detect. But based on observations, the ring stretches across an enormous area. It begins about 128 times the radius of Saturn and extends outward to 207 times the planet's radius. Some estimates suggest it might reach as far as 300 times Saturn's radius. On the inner side, it extends as close as 59 times Saturn's radius, reaching the orbit of the moon, Iapetus. Later studies using other space telescopes, including WISE, Herschel, and Cassini, confirmed its vast size. Observations from WISE suggest the ring might stretch even farther inward, reaching between 50 and 100 times Saturn's radius before fading into the planet's glow. This ring is also incredibly thin compared to its width. Its thickness measures about 40 times Saturn's radius. The particles within it are believed to be very small, with only about 10% of them being larger than 10 centimeters. Scientists believe that these particles likely come from Phoebe itself. Over time, tiny meteors and space debris collide with Phoebe's surface, chipping off dust and ice that then drifts away to form the ring. One of the most fascinating aspects of this ring is that it moves in the opposite direction of most of Saturn's other rings and moons. This is because Phoebe follows a retrograde orbit, meaning it moves backward compared to most other objects around Saturn. As a result, any material coming from Phoebe also follows this unusual orbit. Interestingly, this material eventually falls inward toward Iapetus, another of Saturn's moons. Over millions and even billions of years, this falling dust has slightly darkened the leading side of Iapetus. However, this alone does not explain the moon's striking two-tone appearance. Instead, scientists think the dark material triggers a chain reaction. Once the dark dust settles on part of Iapetus, it absorbs heat from the sun, causing ice in that region to slowly evaporate. This evaporated ice then refreezes onto the colder, brighter areas, making the contrast between dark and light regions even stronger over time. Although the discovery of this massive ring was only confirmed in the 21st century, the idea had been proposed much earlier. Back in the 1970s, an astronomer named Stephen Soter first suggested that a ring of material might exist in this region. His theory remained unproven for decades, until Anne J. Verbisser, Michael F. Skrutsky, and Douglas P. Hamilton finally discovered the ring using NASA's Spitzer telescope. Interestingly, these three scientists had all been graduate students at Cornell University at the same time. As time passes, material from this ring continues to drift inward. Because sunlight heats the tiny dust particles, they gradually move closer to Saturn at a speed that depends on their size. A small grain, about 3 centimeters across, would take the entire age of the solar system to travel from Phoebe to Iapetus. The dark material falling onto Iapetus has also been compared to a similar phenomenon seen on the distant moons Oberon and Titania, which orbit Uranus. Even though these moons are in a completely different part of the solar system, they show the same kind of reddish and darkened leading hemispheres, likely due to similar processes of dust accumulation and surface changes over time. Neptune, the distant ice giant, is surrounded by a fascinating system of rings, primarily consisting of 5 main ones. These rings were first detected on the 22nd of July in the year 1984. 2 teams of astronomers, one led by André Brahic and the other by William B. Hubbard, made this discovery while observing a star being blocked by Neptune's rings from 2 observatories in Chile. However, the first clear images of the rings did not appear until the year 1989, when NASA's Voyager 2 spacecraft flew past Neptune and captured detailed pictures. Unlike Saturn's bright and massive rings, Neptune's rings are thin, faint, and dusty, making them difficult to see. In fact, they are more similar to Jupiter's delicate ring system than to Saturn's grand structures. The rings are named after astronomers who made significant contributions to the study of Neptune. These include Gale, Leverrier, Lassell, Arago, and Adams. Additionally, there is a faint, unnamed ring that coincides with the orbit of one of Neptune's moons, Galatea. 3 other moons, Naiad, Thalassa, and Despina, move through the gaps between these rings. Neptune's rings contain a high percentage of fine dust particles, ranging from 20% to 70%, and they appear to be made of very dark material. Scientists believe that this material is a mix of ice and organic compounds altered by radiation, similar to the rings of Uranus. Among the rings, the Adams ring is the most unique, as it contains 5 distinct arcs, curved segments rather than full circular bands. These arcs, named Fraternité, Égalité 1 and 2, Liberté, and Courage, have remained remarkably stable since their discovery in the year 1980. Scientists are still debating exactly how they maintain their shape, but it is likely that the gravitational pull of Neptune's moon Galatea plays a role in keeping them in place. The idea that Neptune might have rings dates back to the year 1846, when William Lassell, the astronomer who discovered Neptune's largest moon, Triton, thought he had spotted a ring around the planet. However, his claim was never confirmed and was likely a mistake. The first solid evidence of a ring came much later, in the year 1968, when astronomers observed a star dimming momentarily as it passed behind Neptune. However, this finding went largely unnoticed until the year 1977, when rings were discovered around Uranus. Inspired by this, a team of scientists led by Harold J. Reitzema from Villanova University began searching for rings around Neptune. On the 24th of May in the year 1981, they observed a brief dimming of a star, but the pattern of dimming did not match what would be expected from a ring. It was only after the Voyager 2 spacecraft's flyby that scientists realized this dimming had been caused by a small moon of Neptune named Larissa. During the early 1980s, observing Neptune's rings from Earth was particularly challenging because Neptune was not aligned with dense star fields, unlike Uranus. In the year 1983, another attempt to detect the rings produced uncertain results. Over the next 6 years, about 50 similar observations were made, but only about 1/3 of them showed signs of a ring system. It was clear that something was surrounding Neptune, but astronomers could not determine its full shape. The Voyager 2 flyby in the year 1989 finally confirmed the existence of Neptune's rings, solving a long-standing mystery. During its close approach, passing just 4,950 kilometers above Neptune's atmosphere on the 25th of August, Voyager 2 revealed that earlier observations had detected the arcs within the Adam's ring. Since then, advancements in telescope technology have allowed scientists to observe Neptune's rings from Earth. The Hubble Space Telescope and ground-based observatories have captured images of the brighter rings, Adams and Leverrier, though the fainter rings remain difficult to detect. In the year 2022, the powerful James Webb Space Telescope successfully imaged Neptune's rings, providing the first clear view of the faintest ones since Voyager 2's visit. Neptune's 5 main rings, Gale, Leverrier, Lassell, Arago, and Adams, are arranged in increasing distance from the planet. In addition to these well-defined rings, there may be an extremely faint, broad sheet of material stretching from the Leverrier ring toward the planet. 3 of Neptune's rings are narrow, each less than 100 kilometers wide, while the Gale and Lassell rings are much broader, stretching between 2,000 and 5,000 kilometers across. The Adams ring is unique because, in addition to its continuous ring structure, it also contains the 5 bright arcs. The names of 4 of these arcs, Fraternité, Égalité 1 and 2, and Liberté, come from the famous motto of the French Revolution: liberty, equality, fraternity. These arcs were originally discovered in stellar occultation events in the years 1984 and 1985. 4 of Neptune's small moons orbit within the ring system. Naiad and Thalassa move in the gap between the Gale and Leverrier rings. Despina orbits just inside the Leverrier ring, and Galatea lies slightly inside the Adams ring, embedded in an extremely faint ringlet. Compared to Saturn and Uranus, Neptune's rings contain a much higher proportion of dust, making them more similar to Jupiter's faint rings. The particles within Neptune's rings are believed to be made of a dark, reddish material, likely a mixture of ice and radiation-processed organics. The rings are quite transparent, meaning they do not block much light, and their optical depth is very low, generally less than 1/10. Scientists believe that Neptune's rings, like those of Uranus, are relatively young compared to the age of the solar system. Their formation is thought to have been the result of collisions between small moons, which shattered and created the ring material. This idea is supported by the presence of faint, dusty bands similar to those observed by Voyager 2 in the ring system of Uranus. The innermost ring is called the Gala ring, named after Johann Gottfried Galle, the astronomer who first spotted Neptune through a telescope in the year 1846. This ring is quite faint and stretches about 2,000 kilometers across, orbiting the planet at a distance between 41,000 and 43,000 kilometers. It is mostly made up of fine dust, making up somewhere between 40 and 70% of its composition. Moving outward, the next ring is the Leverrier ring, named after Urbain Le Verrier, the scientist who mathematically predicted Neptune's location in the same year, 1846. This ring is much narrower, only about 113 kilometers wide, and orbits Neptune at roughly 53,200 kilometers. It is also composed of a significant amount of dust, making up between 40 and 70% of its structure. A small moon named Despina, which orbits just inside this ring at about 52,526 kilometers, is believed to act as a shepherd, helping to keep the ring stable and in place. Beyond this lies the broadest ring in Neptune's system, known as the Lassell Ring or the Plateau, named after William Lassell, the astronomer who discovered Neptune's largest moon, Triton. This ring appears as a wide, faint sheet of material stretching from the Leverrier ring at around 53,200 kilometers to another ring called the Arago ring at 57,200 kilometers. Its dust content is estimated to be between 20 and 40%. Near the outer edge of the Lassell ring, there is a slightly brighter region at around 57,200 kilometers from Neptune. Some scientists refer to this as the Arago ring, named after François Arago, a French mathematician, physicist, astronomer, and politician. However, this ring is not widely mentioned in many studies. The outermost and best-studied ring of Neptune is the Adams ring, named after John Couch Adams, who independently predicted Neptune's location. This ring orbits at approximately 63,930 kilometers from the planet. It is relatively narrow, measuring about 35 kilometers across, with some areas ranging between 15 and 50 kilometers. Unlike the other narrow rings, the Adams ring contains a lower percentage of dust, estimated to be between 20 and 40%. A small moon called Galatea, which orbits at 61,953 kilometers, acts as a shepherd moon, helping to keep the ring's particles in place. Galatea's gravity also creates patterns in the ring, forming 42 evenly spaced ripples, which have helped scientists estimate the moon's mass. One of the most fascinating features of Neptune's rings is the presence of mysterious arcs within the Adams ring. These arcs are bright, clustered sections of the ring where particles seem to be grouped together rather than spread out evenly. There are 5 main arcs positioned in a narrow band between 247 and 294 degrees in longitude. They have unique names: Fraternité, which is the brightest and longest, Courage, which is the faintest, along with Liberté, Égalité 1, and Égalité 2. When Voyager 2 flew past Neptune in the year 1989, it captured detailed images showing that these arcs are not smooth but clumpy, with small bright spots spaced roughly 100 to 200 kilometers apart. These clumps might contain larger objects, but they are definitely packed with tiny dust particles as their brightness increases when backlit by the sun. The arcs have remained surprisingly stable over time. They were first detected from Earth in the 1980s, then observed again by Voyager 2, and later studied by the Hubble Space Telescope and ground-based telescopes between 1997 and 2005. However, some changes have been noted. Since 1986, the overall brightness of the arcs has faded. The Courage arc shifted forward by 8 degrees, likely jumping to another stable orbit, while the Liberté arc had almost disappeared by 2003. The brightness of the Fraternité and Égalité arcs has fluctuated, likely due to dust moving between them. The existence of these arcs is a scientific puzzle. According to the basic laws of motion, the particles should have dispersed into a uniform ring over time. Several theories have been proposed to explain why they remain clustered. One idea is that Galatea's gravitational influence creates stable zones where the arcs can persist. Another theory suggests that a small, yet-to-be-discovered moon might be trapping the arcs in its gravitational pull. A third possibility is that several tiny moonlets within the ring are helping to maintain the arcs while also supplying them with fresh dust. In the late summer of the year 1989, the Voyager 2 spacecraft passed by Neptune and closely studied its rings. During this flyby, scientists used optical imaging, special cameras that capture light to take detailed pictures of the rings. They also analyzed how the rings blocked or dimmed light when Neptune passed in front of distant stars, using both ultraviolet and visible light to gather information. Voyager 2 observed the rings from different angles in relation to the Sun, capturing how the light scattered in various ways, whether bouncing straight back, passing through at an angle, or spreading in all directions. These images helped scientists understand how the rings reflect sunlight, revealing details about their brightness and the way their particles reflect and absorb light. This in-depth study also led to an exciting discovery. Voyager 2 found 6 previously unknown moons orbiting Neptune. Among them was Galatea, a moon that plays a crucial role in shaping the Adam's ring, acting like a shepherd by keeping its particles in place.